Hello and welcome to Sleepy Science. Tonight we are entering a realm where the rules that make your everyday world feel stable begin to quietly break apart. The quantum foundations of reality itself. Beneath every object you touch, every color you see, every breath you take, particles exist as structured possibilities. Cross barriers they should never classically overcome, behave like waves, form connections across enormous distances, and sometimes lose the very idea of having an individual identity. Across 100 unsettling, calming, and deeply thought-provoking quantum facts, we will explore why observation can change what an experiment reveals, how empty space can create measurable forces and even real light, why atoms do not collapse, how the sun depends on quantum tunneling, why matter feels solid despite being mostly open space, and how quantum rules make lasers, electronics, atomic clocks, superconductors, encryption, and emerging quantum computers possible. Some of these discoveries may feel impossible, yet they are not myths, mystical claims, or science fiction. They are among the most precisely tested ideas humanity has ever developed, even though physicists still disagree about what they ultimately tell us reality is. Before we begin, tell me in the comments where you are listening from and which quantum mystery has always disturbed or fascinated you most. And don't forget to like the video and subscribe for more calm, mind-opening journeys through science. Now, allow the familiar world around you to become a little less certain. Let the noise of the day slowly disappear, and let us descend together into 100 quantum facts that may forever change what you believe reality can be. A particle can exist in several possibilities at the same time. Before the smallest pieces of nature are measured, they do not always carry the single, settled story you expect an object to have. A coin on a table is either showing heads or tails, and a planet occupies a particular region of space, but a quantum particle can be described by a state containing several possible outcomes at once. This condition is called superposition, and it does not simply mean that scientists have failed to discover where the particle is hiding. The possibilities are built into the best description physics can give. An electron in an atom, for example, is not quietly waiting at one secret point like a grain of dust concealed in darkness. Its quantum state spreads across a range of possible locations, with some places more likely to produce a detection than others. Only when the electron interacts strongly enough with a measuring device does one definite result appear. You never observe half of one outcome and half of another. You record a complete event at a particular place. Yet when the experiment is repeated many times under identical conditions, the full pattern of possibilities slowly becomes visible through the distribution of results. This is why superposition is more than ignorance. If the particle had possessed one ordinary hidden condition all along, the experiments would not produce the interference and statistical patterns that laboratories repeatedly observe. Still, it is important not to imagine a tiny object making conscious choices or physically splitting into several miniature copies. Quantum theory describes what may be found and how those possibilities combine, while remaining strangely quiet about what the particle is doing between preparation and measurement. That silence is one of the deepest features of the theory. You are given an extraordinarily accurate map of possible encounters, but not a familiar picture of an object following one secret route through the world. The lesson is subtle. At the foundations of matter, possibility is not merely a sign of human uncertainty. It appears to be part of nature's structure. The solid world surrounding you is therefore built from entities whose futures can remain open until an interaction forces a particular answer, as though certainty is not the starting point of reality, but something that gradually emerges from it. The double-slit experiment changes. When the particle's path is observed, send individual particles toward two narrow openings, and nature quietly produces a pattern that no collection of ordinary pellets should be able to create. When electrons, photons, or even certain large molecules pass through a double-slit apparatus without any device revealing which opening they used, their detections gradually form alternating bands of high and low probability. Each particle arrives as one localized mark, Yet after many arrivals, the marks build an interference pattern, the familiar signature of waves overlapping. The astonishing point is that the particles can be released one at a time. There does not need to be another particle present for the pattern to appear. The quantum possibilities associated with the two routes combine, strengthening some destinations and cancelling others. But when equipment is added that can determine which slit each particle passed through, the interference disappears. The final screen begins to resemble the result expected from separate particles taking identifiable routes. This change is often described carelessly, as though a human mind frightens the particle into behaving differently. The real explanation is more physical and more revealing. To obtain path information, the particle must become correlated with a detector, a photon, an atom, or some other part of the surrounding world. That interaction marks the alternatives differently, preventing them from remaining coherent enough to interfere. No conscious observer needs to stare at the apparatus. Even information recorded and never read can be sufficient if the two paths become physically distinguishable. The experiment, therefore, teaches something more precise than the slogan that observation creates reality. It shows that knowledge in quantum physics cannot be separated from the interactions required to obtain it. You may choose to preserve information about interference, or you may arrange the experiment to reveal the path, but you cannot fully keep both kinds of evidence at once. Nature does not seem to offer a hidden classical movie in which the particle travels through one slit, while somehow pretending to behave like a wave. Instead, the design of the experiment determines which relationships can remain visible. What looks like a simple barrier with two openings becomes a quiet demonstration that reality cannot always be divided into an untouched object on one side and a passive observer on the other. The question you ask must be asked physically, and the act of asking becomes part of the answer. Quantum entanglement connects particles across enormous distances. Two particles can travel so far apart that light would need years to cross the distance between them. Yet certain measurements can still reveal correlations stronger than any ordinary shared plan can explain. This phenomenon, known as quantum entanglement, begins when particles are prepared or interact in a way that gives them one combined quantum state. Afterward, it may no longer be correct to describe each particle as carrying its own complete set of independent properties. The meaningful description belongs to the pair. Suppose two entangled particles are sent in opposite directions, and their spin-like properties are measured along carefully chosen orientations. Each individual result appears unpredictable. One laboratory cannot know in advance what answer it will receive, but when the records from both laboratories are later compared, the outcomes follow patterns that quantum mechanics predicts with remarkable precision. Experiments testing. Bell's inequalities have shown that these correlations cannot be explained by a simple model in which each particle left the source carrying a private list of predetermined answers for every possible measurement. The connection is therefore deeper than two matching envelopes opened in distant rooms. Yet entanglement does not allow a message to be sent faster than light. The observer on either side sees a random sequence and cannot control the result well enough to encode information. Only after the two sets of data are brought together through ordinary communication does the hidden structure of the correlation become clear. This distinction matters because entanglement is extraordinary without breaking every rule of relativity. It does not act like an invisible signal racing through space. Instead, it suggests that the quantum state of a system can be fundamentally non-local, meaning that the complete description cannot always be divided into separate pieces assigned to separate locations. Today, this is not merely a philosophical curiosity. Entanglement is tested in laboratories, distributed through optical fibers and satellites, and used in emerging forms of quantum communication, sensing, and computation. Still, its deepest meaning remains unsettled. You can calculate what the particles will do together, but ordinary language struggles to explain how distant objects can behave as parts of one indivisible system. Perhaps the discomfort comes from expecting separation in space to guarantee separation in reality. Entanglement shows that this expectation is not always justified. Distance can separate the particles, the detectors, and the people watching them, while the mathematical relationship that defines the pair remains whole. At the smallest scales, the universe may be composed not only of objects occupying places, but of connections that cannot be completely assigned to any single place at all. A particle can pass through a barrier. It should never be able to cross. A wall that would stop every ordinary object can become strangely permeable when the traveler is small enough. In classical physics, a particle without sufficient energy to cross a barrier must remain trapped on its original side, just as a ball rolling toward a hill must fall backward if it cannot reach the top. Quantum particles are not confined to such a simple picture. Their state can extend into the forbidden region and, if the barrier is thin enough, reach beyond it. This gives the particle a measurable chance of appearing on the other side without ever possessing the classical energy required to climb over the obstacle. The process is called quantum tunneling. Although the particle does not carve a tunnel, break the barrier, or borrow a hidden burst of energy, the probability depends strongly on the particle's mass, the barrier's thickness, and how difficult the crossing would normally be, which is why tunneling is common for electrons and nuclei, but effectively invisible for people, stones, and other large objects. Experiments can prepare enormous numbers of apparently identical particles and find that some remain trapped while others emerge beyond the barrier, with the overall rate matching quantum predictions. This phenomenon is not a rare curiosity confined to theoretical laboratories. It contributes to radioactive decay, chemical reactions, microscopic electronics, and several instruments capable of examining individual atoms. The unsettling lesson is not that matter can casually ignore every boundary, but that a forbidden path in everyday physics may become an unlikely path in quantum physics. At nature's smallest scales, cannot happen often means something quieter and more precise. It can happen, but only with a probability that the universe decides through rules too subtle for ordinary intuition. The sun shines because quantum tunneling makes the impossible possible. Deep inside the sun, an event that should be nearly impossible happens often enough to illuminate every sunrise you have ever seen. The solar core is intensely hot and compressed, yet even there, positively charged protons repel one another so strongly that classical calculations would rarely allow them to approach closely enough to fuse. To begin the proton-proton chain that powers the sun, two protons must enter the extremely short range where nuclear forces can act. Quantum tunneling provides that narrow opening. A tiny fraction of the countless protons colliding in the core cross the electrical barrier they could not classically overcome, allowing nuclear reactions to begin and eventually transforming hydrogen into helium. The first stage is extraordinarily slow because it also involves the weak nuclear interaction. And this apparent inefficiency is one reason the sun does not consume its fuel in a brief, catastrophic flash. One proton may endure an immense number of encounters before participating in fusion, but the sun contains so many particles that successful reactions are occurring continuously throughout its core. The energy released does not travel immediately to Earth. It is first carried through the crowded solar interior, repeatedly absorbed and re-emitted, before finally escaping as light and heat. In this way, a microscopic probability becomes a cosmic source of stability. The sunlight resting on your skin began with particles crossing barriers that ordinary reasoning said they could not cross. Yet the process is neither miraculous nor lawless. It follows quantum mechanics with remarkable consistency. The sun, therefore, offers a quiet correction to human intuition. Events can be individually unlikely and still become inevitable when nature is given enough particles, enough collisions, and enough time. Quantum physics can detect an object without directly touching it. Imagine discovering an object precisely because a detector received a photon that never struck it. This is the counterintuitive idea behind interaction-free measurement, first illustrated through the Elitzer-Weidmann bomb tester. Picture an extremely sensitive device that would explode if even one photon touched its trigger, making ordinary inspection impossible. A carefully arranged interferometer divides the photon's possible route into two arms and later recombines them. When both paths are clear, their wave-like contributions cancel at one particular detector, leaving that detector dark. Place the sensitive object in one path, however, and the balance is disturbed. Sometimes the photon enters the blocked route and is absorbed, causing the feared interaction. But in a successful trial, the photon reaches the normally dark detector instead. That click reveals that something blocked one path, even though the object did not absorb the photon during that successful run. The method does not mean that every object can be examined with absolutely no physical consequences, and the phrase interaction-free remains technically debated. Some trials do involve absorption, and the apparatus must still be prepared, so the object could have affected the result. What quantum physics allows is more precise. Information about the object's presence can sometimes be obtained without the probing particle exchanging energy with or being absorbed by that object in the detected event. Improved versions can greatly reduce the chance of damaging delicate samples by repeatedly and gently testing the available paths. This turns absence into evidence. You learn not from a direct collision, but from a pattern that should have remained impossible if the hidden object were not there. The deeper surprise is that an unrealized interaction can still shape what becomes observable, reminding you that quantum experiments are influenced not only by what physically occurs, but also by which alternatives the arrangement allows to occur. A single particle can interfere with its own possible paths. Release one particle into an experiment, remove every other particle from its surroundings, and something still appears to compete with it on the way to the detector. Its own unrealized possibilities. When an electron, photon, neutron, or even a sufficiently isolated molecule is given several available routes, quantum mechanics does not describe it as secretly selecting one path in the ordinary way. Instead, each possible route contributes a wave-like amplitude carrying both strength and phase, and these contributions meet before the final detection occurs. Where they reinforce one another, an arrival becomes more likely. Where they cancel, an arrival can become extremely unlikely or disappear from the pattern altogether. Only one localized event is recorded in each trial, so the detector never displays a blurred fraction of a particle. Yet when the experiment is repeated one particle at a time, the individual marks slowly arrange themselves into bright and dark regions that could not be produced by particles following independent classical trajectories. This has been demonstrated with many kinds of quantum objects, including electrons sent separately through carefully controlled instruments. Saying that the particle interferes with itself does not mean a tiny solid object literally breaks into visible pieces and collides with its copies. It means the alternative ways the event could occur remain physically connected in the quantum description, allowing their phases to combine before one outcome is registered. The experiment therefore reveals something subtle about possibility. Alternatives that never become separate observed events can still influence the event that finally happens. You see only one arrival, but the location of that arrival carries the faint mathematical imprint of routes that were available and never individually witnessed. At this scale, the unrealized is not always irrelevant. Sometimes, it quietly shapes the boundary of what becomes real. Measuring a quantum system changes what can be known about it. The closer you force nature to answer one precise question, the more quietly another answer can slip beyond your reach. A quantum measurement is not simply a camera taking a neutral photograph of properties that were all fully defined beforehand. It is a physical process that establishes a relationship between the system and an apparatus, producing a stable record of one chosen feature. If an experiment is designed to determine a particle's position very sharply, the resulting state generally contains less definite information about how its momentum is distributed. If another arrangement is chosen to reveal a delicate phase relationship, creating a permanent record of a competing property may destroy access to that phase. This is not merely because the equipment is clumsy, nor because scientists have failed to build instruments gentle enough. Quantum theory places limits on which properties can possess simultaneously sharp operational meaning, and the measurement setup helps determine which kind of answer can appear. Different instruments are not simply revealing different pages of a complete hidden file. They can define different experimental contexts that cannot all be combined without changing the system. Even the most carefully designed detector must interact in some way, because information cannot enter the outside world without becoming encoded in light, electrical current, atomic motion, or another physical record. Once that record exists, some earlier possibilities may no longer remain available for later comparison. This does not mean reality is created by human attention, or that you can alter particles through thought alone. The change comes from physical interaction, amplification, and the formation of information that can persist. Yet the philosophical weight remains. Knowing is not always separate from doing. In quantum physics, the method used to ask a question helps establish what can meaningfully be answered, reminding you that complete knowledge may not be a hidden treasure waiting untouched, but a set of perspectives that cannot all be held with equal sharpness at the same moment. Particles behave like waves until a definite result is recorded. Quantum object can spread through an apparatus like a wave, bend around edges, and form diffraction patterns. Yet the moment it leaves a lasting trace, it appears at one specific place. This dual character becomes especially clear when electrons or neutrons pass through the regularly spaced atoms of a crystal. Before detection, their quantum states propagate in a way that allows different portions of the state to combine, producing directions where arrivals are favored and others where they are suppressed. The overall behavior resembles the diffraction of water or light waves, and scientists use these patterns to study the hidden structure of materials. But the detector does not receive a thin mist of partial electrons distributed across the screen. It records a complete localized event, a flash, a pulse of current, an altered atom, or another definite physical mark. As more particles arrive, these separate points gradually reveal the broader wave-like distribution that guided their probabilities. It is tempting to say that the particle begins as a wave and suddenly transforms into a tiny object, but this can be misleading. Wave and particle are classical words borrowed from the visible world, while a quantum entity fits neither picture completely. Its state evolves according to wave-like rules, but interactions that create durable records produce discrete outcomes. A human being doesn't need to watch the detector, and consciousness does not perform the transformation. What matters is that the quantum system becomes irreversibly linked with a larger environment capable of preserving the result. The wave-like alternatives then cease to remain available as one coherent whole, while a particular event becomes part of ordinary history. You are left with a world built from two layers of description, a quiet landscape of distributed possibilities, and the sharp, singular marks through which those possibilities become known. The mystery is not that nature cannot decide whether it is made of waves or particles, but that both familiar images are incomplete shadows of something more fundamental. Quantum reality is described by possibilities rather than certainties. Beneath every definite event you witness lies a quieter layer in which physics offers no guaranteed prediction for what will happen next. Classical science can often tell you where a planet will be years from now, or how a falling object will move, provided its starting conditions are known well enough. But quantum mechanics works differently. Even when scientists prepare many particles in exactly the same way and control the experiment with extraordinary care, the theory may predict only the chances of several possible results. It can say that one outcome should appear frequently, another occasionally, and a third almost never, yet it may not identify which result the next individual particle will produce. This does not make quantum mechanics vague or unreliable. Its probabilities are among the most accurately tested predictions in all of science. When an experiment is repeated thousands or millions of times, the results settle into the precise statistical pattern the theory describes. Much as countless raindrops can form a stable landscape, even though no one can name the exact spot where the next drop will land. Scientists still debate whether this uncertainty is truly fundamental or whether some deeper description remains hidden beneath current theory, but experiments have severely restricted the simplest attempts to restore an ordinary, predetermined reality. Quantum physics therefore asks you to rethink what a successful law of nature must provide. Perhaps the universe does not always contain a single future waiting to be uncovered. Perhaps, at its deepest level, physical law governs the structure of what may happen rather than announcing what must happen. Certainty then becomes something that belongs more naturally to large patterns than to isolated events. And the world you experience appears stable not because chance has vanished, but because enormous numbers of uncertain processes quietly average themselves into dependable order. 2. Entangled particles can behave like parts of one shared system. Separate two entangled particles, and you may discover that the distance between them is easier to describe than the boundary between them. In ordinary thinking, every object should possess its own complete condition. One particle has its properties, the other has different properties, and the total system is merely the two descriptions placed side by side. Entanglement breaks that expectation. The pair can possess a perfectly defined relationship, even when neither particle has an equally complete individual description. For example, two particles may be prepared so that their combined spin is balanced, while the outcome for either particle alone remains uncertain. Before measurement, it is not always accurate to imagine that each one secretly carries a fixed answer. What is definite is the rule connecting their possible answers. The information belongs to the pair as a whole. This is why examining only one member can make its behavior appear random, while comparing both sets of results reveals an exact underlying structure. The shared state is not a message passing back and forth, and it does not mean the particles are exchanging thoughts or forces across space. It means quantum theory treats the combined system as more fundamental than the independent pieces we would prefer to assign to it. This principle has practical consequences. Quantum computers use carefully engineered entangled states because the information stored in several qubits can reside in their joint relationships rather than inside any one qubit. Quantum sensing can also use such correlations to detect tiny changes that would be harder to reveal with independent particles. Yet the deeper lesson is not technological. Entanglement shows that knowing everything available about a whole does not always mean you can divide that knowledge neatly among its parts. The universe may contain properties that exist only through relationship, with no single location able to claim them completely. You are accustomed to building wholes from separate pieces, but quantum mechanics sometimes reverses the order. The whole comes first, and the apparent individuals emerge only as partial views of something that was never fully divided. Quantum particle has no single classical path between 2 points. Between the moment a quantum particle leaves a source and the moment it reaches a detector, nature does not provide the continuous trail that your imagination instinctively draws. A thrown stone follows a path through space at every instant, even when no one watches it, and classical physics allows that trajectory to be calculated. A free quantum particle is described differently. The theory assigns contributions to every physically possible way the journey could connect its beginning and end, including direct routes, curved routes, and countless wandering alternatives. This idea is often called the sum over histories, developed most famously by Richard Feynman. It should not be pictured as a tiny bead literally racing along infinite roads at once. Rather, quantum mechanics does not grant any one unmeasured route the status of the actual hidden path. The alternatives contribute different phases, and most of their effects cancel one another. For large objects, the paths near the familiar classical trajectory reinforce more strongly, which is why a baseball, a planet, or your own moving hand seems to follow one smooth and predictable line. At microscopic scales, however, the wider collection of alternatives can leave observable effects. If scientists try to monitor a particle continuously, Each interaction with the measuring apparatus changes the situation and creates a chain of recorded positions. Those marks may resemble a path, but they are a sequence of physical encounters, not the discovery of an untouched trajectory that existed in complete detail beforehand. Even the thin track seen in a particle detector is produced through repeated collisions with surrounding material. The path appears because the environment keeps forcing localized records into existence. Without those records, asking which exact route the particle really took may have no answer within standard quantum theory. This does not mean the particle travels nowhere or that movement is an illusion. It means motion at the quantum level is represented by a rule connecting possible beginnings and endings, rather than by a miniature object carrying a permanent map of its journey. The smooth roads of the everyday world may therefore be an emergent simplification, formed when countless alternative histories cancel into the narrow route your senses recognize as ordinary motion. The quantum eraser can remove information about a particle's path. A pattern can disappear simply because a path could be identified, and return when that identifying information is made impossible to recover. This is the strange but carefully tested principle behind the quantum eraser. In these experiments, a particle such as a photon is sent through an arrangement containing two possible routes, while another part of the apparatus marks which route was taken. The marking does not need to be read by a scientist. Its mere physical availability is enough to destroy the conditions required for interference. Because the alternatives have become distinguishable, the eraser does not travel backward and change what the photon already did, nor does it delete a stored fact from history. Instead, it measures the associated information in a different way, one that no longer reveals which route belonged to which event. When researchers sort the detection records according to those later measurements, complementary interference patterns can appear within separate groups of data. If all the groups are mixed together, however, the patterns cancel and no interference is visible. This detail prevents the experiment from sending messages into the past or rewriting an earlier observation. Nothing unusual appears in the first detector's results until the two sets of records are compared through ordinary communication. The deeper lesson is that quantum behavior depends not only on whether a particle is physically disturbed, but on whether alternative histories have left distinguishable traces in the world. Information is therefore not an abstract label floating above the experiment. It is a physical relationship encoded in detectors, partners, and surroundings. Erase the ability to tell the alternatives apart, and the hidden phase relationships can be revealed in carefully selected correlations. The past is not being changed. Rather, the experiment shows that the meaning of a recorded event may remain incomplete until you know which larger pattern it belongs to. A single mark tells you almost nothing, but the relationships among many marks can reveal a structure that was invisible when the data was viewed as one undivided whole. Repeated measurement can prevent a quantum system from changing. Watch a quantum system often enough, and under the right conditions, the act of repeatedly checking it can slow the very change you are waiting to see. This phenomenon is called the quantum Zeno effect, named after an ancient paradox in which motion seems impossible when a journey is divided into endlessly smaller steps. Imagine preparing an unstable quantum state that would normally evolve into another state over time. If you leave it alone, the probability of change gradually grows. But if you perform a rapid sequence of measurements, asking whether the system is still in its original condition, each successful check prepares it again in a state close to where it began. When the intervals are sufficiently short and the measurements are properly designed, the transition can be greatly suppressed. This does not mean that human attention freezes matter, and it does not allow you to preserve any object forever by staring at it. A measurement must be a real physical interaction, and practical systems continue to face noise, imperfect control, and other routes of decay. Scientists have observed the effect in trapped ions, atoms, and other controlled quantum systems, where frequent probing can inhibit transitions between selected states. There is also an inverse form called the anti-Zeno effect, in which repeated interactions can accelerate change instead of preventing it. The result depends on timing, the surrounding environment, and the details of the system being observed. This makes the phenomenon more subtle than the slogan, "A watched pot never boils." Measurement does not universally stop evolution. It reshapes the conditions under which evolution occurs. The effect now has practical importance in controlling fragile quantum states, protecting information, and guiding systems through selected sequences without allowing unwanted transitions to dominate. It also offers a deeper question about change itself. At the quantum level, development is not always a smooth process unfolding independently in the background. The rhythm at which a system is tested can become part of its dynamics. Sometimes the state changes because time passes. Sometimes it remains because the outside world keeps asking, again and again, whether it is still there. Quantum particles can be entangled after they have already been detected. Two particles that never existed together at the same moment can still produce records displaying the correlations of an entangled pair. This startling result appears in experiments known as delayed choice entanglement swapping. The process begins with two separate entangled pairs. One particle from each pair travels toward an outside detector, while their partners are brought together at a central station. The distant particles may be measured first, producing ordinary-looking results that seem individually random. Later, the central station performs a special joint measurement on the two remaining particles. Depending on the outcome of that measurement, the earlier records from the distant detectors can be sorted into groups. Within certain groups, the results show the correlations expected from particles that were entangled, even though those particles never interacted directly and may already have been detected before the central choice was completed. This does not mean the later experiment physically changes an event that has already happened. The earlier detector records remain exactly as they were, and no observer can examine them alone and discover whether entanglement swapping will later succeed. The significant pattern becomes visible only after the central result is communicated and the data is compared. No usable information travels backward in time, and no message can be sent into the past. What changes is the way the full experiment divides its correlations. Quantum mechanics permits the four-particle system to contain relationships that cannot be understood as independent local stories assigned in advance to each particle. The later joint measurement determines which correlations can be meaningfully identified among records already collected. This is why the experiment feels as though the future has reached backward, even though relativity and ordinary causality remain intact. It challenges the comforting belief that every detection must carry a complete, self-contained history at the moment it occurs. Sometimes the significance of an event belongs not to the event alone, but to a wider network of measurements spread across space and time. The marks were already present, yet the relationship capable of joining them had not become visible until the experiment was viewed as a whole. Identical quantum particles cannot always be treated as separate individuals. Imagine exchanging two particles and discovering that nature contains no physical clue that anything has changed. In everyday life, even perfectly matching objects remain separate individuals. Two coins may look identical, but one can be scratched, followed, numbered, and distinguished from the other. Identical quantum particles are different in a deeper sense. Two electrons of the same type do not merely resemble one another. Quantum theory provides no hidden tag that says, this is electron 1 and that is electron 2. If their positions are exchanged while every measurable condition remains the same, the exchange does not create a new observable arrangement. This becomes important when several identical particles occupy the same system, because their collective quantum state must be built in a way that respects their complete indistinguishability. The particles cannot always be described as independent travelers carrying permanent identities through time. Instead, the system may tell you how many particles are present in particular states without allowing you to say which original particle later appeared at which location. In collisions, atoms, and dense materials, attempting to trace each identical particle as though it were a numbered marble can produce the wrong predictions. What remains physically meaningful is the pattern formed by the entire collection, including how possible exchanges alter that pattern. This does not mean particles merge into one object or stop existing separately when detected. A detector can still register events at different places. The strange point is that the event does not necessarily reveal a continuous personal history belonging to one uniquely identifiable particle. At the quantum level, individuality may not be a fundamental possession carried by every piece of matter. It may emerge only when objects become complex enough to preserve distinctive records, memories, locations, and histories. The smallest constituents of the world can therefore be perfectly real while lacking the private identities you instinctively assign to everything that exists, leaving you to wonder whether being an individual is written into matter itself or slowly created by the stories that matter becomes capable of keeping. Empty. Space contains quantum fields, even when no particles are present. Remove every atom, every photon, and every measurable fragment of matter from a region, and you still have not created absolute nothingness. Modern physics describes the universe as filled with quantum fields that extend throughout space, and those fields remain present even when no particles are detected. The emptiest possible condition is called the vacuum state, but it is not the absence of the physical framework. It is the lowest energy condition those fields can occupy. You can think of it not as an empty box after its contents have been removed, but as the quietest state the box itself is capable of having. Quantum rules prevent this state from behaving like a perfectly motionless classical surface, with every property fixed exactly. Certain quantities retain unavoidable uncertainty, creating subtle vacuum fluctuations in the mathematical description of the fields. These fluctuations are often portrayed as particles constantly appearing and disappearing, but that popular image can be misleading. In many calculations, virtual particles are useful bookkeeping tools rather than tiny objects that can be directly watched jumping out of nothing. What is experimentally important is that the vacuum can influence physical systems. It can alter atomic energy levels, affect how excited atoms release light, and contribute to measurable forces when boundaries restrict which field configurations are allowed. The vacuum also carries profound unresolved questions. Quantum field calculations suggest an enormous contribution to vacuum energy. While observations of the universe's expansion point to a vastly smaller value, creating one of the greatest mismatches between theory and cosmology. Empty space is therefore not merely a blank distance separating meaningful objects. It possesses structure, rules, and measurable consequences of its own. When you look into darkness and imagine that nothing occupies the gap, physics offers a quieter and stranger answer. Particles may be absent, yet the underlying stage has not disappeared. The silence of space is still a physical state, and the fact that it looks empty may reveal more about the limits of your senses than about what is truly there. Particles are ripples moving through invisible quantum fields. What you call a particle may not be a tiny object placed inside the universe at all, but a concentrated disturbance traveling through something that fills the universe everywhere. In quantum field theory, each fundamental kind of particle is associated with a field extending across space. There is an electron field, electromagnetic fields whose excitations are photons, and other fields connected with the known particles of nature. A particle appears when one of these fields carries a discrete, transferable amount of excitation. The comparison to a ripple on water can help, but only if you remember that a quantum field is not known to be made from a hidden material beneath it. The field is part of the fundamental description itself. A photon moving through a vacuum is therefore not necessarily best pictured as a glowing grain flying across an empty container. It is a propagating excitation of the electromagnetic field, capable of transferring a specific packet of energy when it interacts with matter. An electron is likewise not understood as a miniature solid sphere containing some smaller mechanical machinery. It is an excitation of the electron field, displaying properties such as mass, charge, and spin according to the rules governing that field. This perspective explains why particles can be created and destroyed in high-energy reactions without violating conservation laws. When energy is transferred into a field in the right way, new excitations can appear, When particles are absorbed or transformed, their energy and other conserved properties move into different excitations. The universe is not required to preserve a permanent inventory of tiny beads. It preserves deeper quantities while the fields change their patterns. This view also replaces the image of space as a passive stage. Matter and radiation become active states of fields already woven through every region, while what you experience as an object is an organized and remarkably persistent pattern within them. The chair beneath you, the light entering your eyes, and the atoms composing your body are not foreign pieces placed into an empty cosmos. They are structured movements of the cosmos's own underlying fields. You may feel like a solid visitor passing through space, yet at a deeper level, you are space's fields briefly holding a form complex enough to notice their own motion. A vacuum can produce measurable forces between metal surfaces. Bring two uncharged metal surfaces extremely close together, and an invisible force begins to draw them toward one another, even though no ordinary attraction was deliberately placed between them. This is the Casimir effect, predicted in 1948 and later measured with increasing precision. The space between the surfaces and the space outside them do not allow the electromagnetic field to behave in exactly the same way. Between closely spaced plates, only certain patterns of the field can fit, while a broader range is available outside. This difference in the permitted field configurations creates a tiny imbalance of pressure, producing a measurable force. The plates are not being pulled together by little particles striking them from the vacuum, and the effect does not provide unlimited energy from nothing. It is better understood as a change in the energy of the entire arrangement when the boundaries restrict the field. The force becomes much stronger as the separation shrinks, which is why it matters most at microscopic and nanoscopic distances. In real experiments, scientists must carefully account for temperature, surface roughness, electrical patches, and the actual properties of the materials, because these can alter or imitate part of the measured attraction. Yet after those complications are controlled, the effect remains. It has become relevant to the design of tiny machines, where components placed too close together can unexpectedly stick. What appears to be an empty gap can therefore influence the motion of solid objects on either side of it. The lesson is not that the vacuum is a mysterious substance pushing metal around, but that boundaries can change the physical state of fields and turn an apparently vacant distance into an active part of the experiment. Even a space containing no detectable particles can help decide whether two objects remain apart or quietly move together. Empty space can produce real light when its boundaries change rapidly. Move the boundary of an electromagnetic field quickly enough, and darkness can answer by releasing detectable photons. This phenomenon is known as the dynamical Casimir effect, and it is related to the ordinary Casimir force, but involves a rapidly changing system rather than two stationary surfaces. A perfectly still boundary helps determine which field patterns are allowed in a region. If that boundary changes slowly, the field can adjust without producing much excitement. But when the conditions change extremely rapidly, the field may not remain in its lowest energy state. The disturbance can convert energy supplied by the moving or modulated boundary into real photons that travel away and can be detected. Physically moving a metal mirror fast enough is extraordinarily difficult, so researchers have reproduced the effect in superconducting electrical circuits. By changing the electrical properties of a circuit at immense speed, they created the equivalent of a mirror whose effective position moved rapidly. The circuit then emitted pairs of microwave photons with correlations expected from the dynamical Casimir process. This does not mean empty space creates energy for free. The energy of the light comes from the external equipment driving the rapid change. The vacuum provides the quantum starting condition through which that supplied energy becomes radiation. The effect also differs from heating an object until it glows, because the photons emerge from a controlled alteration of the field's boundary conditions, rather than from ordinary thermal motion. You can think of it as changing the rules of a silent instrument so abruptly that the instrument can no longer remain silent. Nothing material was waiting inside as stored light, yet the field was capable of responding when its environment changed. The experiment reveals that emptiness is not simply a passive absence awaiting matter. Under carefully engineered conditions, changing the shape of what the vacuum is allowed to do can transform mechanical or electrical work into genuine light, showing that even darkness has a structure that can be disturbed. Quantum information cannot be perfectly copied. There is no universal quantum photocopier capable of taking an unknown state and producing two flawless versions while leaving the original intact. This restriction is called the no-cloning theorem, and it separates quantum information from the ordinary information stored in books, photographs, and computer files. A classical bit can be read and copied repeatedly because it already carries a definite value that can be duplicated without changing its meaning. An unknown quantum state may contain a delicate combination of possibilities, including relative phases that determine how it will behave in future experiments. Any machine capable of copying every possible state would have to respond correctly not only to a set of simple states, but also to every combination of them. The rules governing quantum evolution make those demands incompatible. A device that copies certain distinct states correctly cannot automatically copy all their possible mixtures in the same way. This is a mathematical limit of the theory, not merely a failure of current engineering. It does not prevent scientists from preparing many systems in the same known state because they can repeat the known preparation procedure. Nor does it forbid imperfect copying restricted sets of distinguishable states, or transferring a quantum state through teleportation. Quantum teleportation avoids the rule because the original state is destroyed as the state is reconstructed elsewhere, so two perfect versions never exist simultaneously. The no-cloning theorem has powerful practical consequences. It helps protect quantum communication, because an eavesdropper cannot secretly duplicate unknown quantum signals, keep perfect copies, and forward untouched originals without leaving evidence. It also makes quantum computers difficult to protect, since fragile qubit information cannot simply be backed up in the ordinary way. Error correction must spread information across carefully designed relationships rather than clone individual qubits. At a deeper level, this rule gives quantum information an unusual kind of uniqueness. A state can be transmitted, transformed, or lost, but it cannot always be multiplied without consequence. In a world where almost every message can be copied endlessly, nature preserves certain descriptions as singular events, reminding you that complete knowledge does not always come with the power to reproduce what has been known. A quantum state cannot be measured completely without disturbing it. An unknown quantum state can hide more information than a single measurement is ever allowed to reveal. When you measure a quantum system, the apparatus does not simply look inside and copy a complete description of what was already there. It forces the system to produce one result associated with the particular question the instrument was built to ask. Measuring a photon's polarization in one orientation, for example, gives a definite outcome in that orientation, but the process generally leaves the photon in a new state connected to the measurement. Any delicate information about other possible orientations may be altered or lost. This is why scientists cannot take one unknown particle, examine it once, and reconstruct its entire quantum state. To determine a state experimentally, they use quantum tomography. They prepare many systems in the same way, measure different members of the group with different settings, and combine the statistics. The original state is inferred from the collection rather than extracted intact from one individual system. The disturbance is not always a violent physical impact. It can be caused by the unavoidable fact that obtaining information requires the particle to become correlated with a detector. Some specially prepared states can be measured repeatedly without changing the same measured property. But no universal method can reveal every feature of an arbitrary unknown state while leaving it untouched. Quantum knowledge therefore has a cost. The more completely you try to describe a fragile system, the more you must rely on many similarly prepared versions rather than one perfectly preserved original. At this scale, observation is not the opening of a sealed box. It is an encounter that leaves both knowledge and change behind. Electrons do not orbit atomic nuclei like tiny planets. The familiar picture of electrons circling an atomic nucleus is useful for a school diagram, but nature never built the atom as a miniature solar system. A planet follows a continuous route around the sun and can, in principle, be located at every moment along that path. An electron bound inside an atom is described by an orbital, which is not an orbit and not a blurred photograph of a rapid circular motion. An orbital is a quantum state that tells scientists how likely a measurement is to find the electron in different regions around the nucleus. Some orbitals are spherical, others form lobes, rings, or more complicated shapes, and these patterns arise from the wave-like structure of the electron's state. Even the electron's angular momentum does not mean it is secretly tracing a classical loop. It appears only in specific allowed amounts and behaves according to rules with no exact planetary equivalent. The old orbiting model also creates a serious problem. In classical physics, an electrically charged object moving in a curved path should radiate energy, lose speed, and spiral inward. Real electrons in stationary atomic states do not continuously radiate in this way. They remain described by stable spatial patterns until an interaction causes a transition. You should not imagine an electron as a tiny marble concealed somewhere inside its orbital cloud, following a route that physics has simply failed to observe. Standard quantum mechanics does not assign it that ordinary hidden trajectory. The atom is therefore not a mechanical clockwork device made smaller than your eyes can see. It is a system whose structure is defined by standing quantum patterns, reminding you that shrinking an everyday picture does not necessarily bring you closer to reality. Atoms remain stable because electrons occupy quantum states. Every object around you survives because an electron cannot surrender energy forever and collapse without limit toward an atomic nucleus. The electrical attraction between a negatively charged electron and a positively charged nucleus pulls them together. So classical reasoning might suggest that the electron should fall inward until the atom destroys itself. Quantum mechanics prevents this by allowing bound electrons to occupy only particular energy states. Among them is a lowest state, called the ground state, below which the electron cannot descend while remaining part of that atom. Trying to confine the electron into an ever smaller region would also make its momentum increasingly uncertain, raising its kinetic energy rather than producing a motionless particle sitting inside the nucleus. Stability emerges from a balance between electrical attraction and the quantum cost of extreme confinement. An atom can absorb energy and move an electron into a higher state, but the electron later returns by releasing a photon whose energy matches the gap between the states. It does not slide smoothly through every value in between. These discrete levels give each element a characteristic spectrum, allowing astronomers to identify atoms in distant stars by the precise colors they absorb or emit. The ground state does not mean the electron has stopped moving like a tiny resting object. It means the atom has reached its lowest permitted quantum arrangement. Under ordinary conditions, there is simply nowhere lower for it to go. The firmness of matter begins with this quiet restriction. Tables, oceans, air, and living cells persist because nature does not offer electrons an endless staircase downward. Atomic stability is not maintained by rigid supports hidden inside matter, but by rules that define which states are physically allowed and where the descent must end. Solid matter is held together by quantum rules. The floor beneath your feet feels perfectly solid, yet almost none of its volume is filled with anything resembling hard material. Atoms consist largely of spacious regions surrounding tiny nuclei, so the firmness you experience cannot be explained by miniature pieces packed together like stones in a wall. Solidity emerges from quantum rules governing how electrons respond when atoms approach one another. In a solid, negatively charged electrons and positively charged nuclei create electrical attractions and repulsions, while electron states spread across atoms and sometimes form shared bonds. These bonds arrange matter into stable structures such as crystals, metals, glass, and biological tissue. When you press your hand against a table, the atoms in your skin do not make direct mechanical contact with the table's nuclei. Instead, the electron distributions in the two materials resist being pushed into an energetically unfavorable arrangement. Electromagnetic repulsion becomes important, but quantum behavior determines how those electrons are organized, how strongly atoms bind, and how the material responds to pressure. In a metal, some electrons can move through the larger structure, helping the material conduct electricity and allowing its atoms to remain joined in a flexible lattice. In diamond, electrons participate in strong directional bonds that create exceptional hardness. In rubber, long molecular chains can bend, stretch, and return toward their earlier shapes. The different sensations of steel, wood, salt, ice, and skin therefore arise from different quantum arrangements rather than from different degrees of microscopic fullness. Solidity is not a single substance hidden inside matter. It is a stable pattern of forces, allowed states, and collective behavior. The world feels firm because its smallest components follow invisible restrictions with extraordinary consistency, turning mostly open atomic space into surfaces that can support buildings, carry footsteps, and give your body a place to rest. The Pauli exclusion principle prevents matter from collapsing into itself. Your body occupies its own volume because electrons obey a rule that never announces itself to your senses. The Pauli exclusion principle states that identical fermions, including electrons, cannot occupy exactly the same quantum state within the same system. This does not mean two electrons can never be close together, nor does it describe an ordinary force pushing them apart like magnets. It means that when several electrons belong to an atom or material, they must differ in some aspect of their quantum condition. As the lowest available states become occupied, additional electrons are forced into other states with different energies or spatial patterns. This creates the layered electron structure of atoms and contributes to the resistance matter develops when compressed. If electrons were free to collect in one lowest state, atomic structures would be radically smaller, chemical variety would largely disappear, and familiar matter could not maintain its present form. The exclusion principle also explains a special kind of pressure called degeneracy pressure. When matter is squeezed intensely, as in the interior of a white dwarf star, electrons are crowded into a smaller region, but cannot all settle into identical states. They must fill states associated with increasingly greater momentum, producing resistance to further compression even when ordinary heat is no longer the main support. In sufficiently massive stellar remnants, gravity can overcome electron degeneracy pressure, but its ability to delay collapse shows that the same quantum rule shaping ordinary atoms can help support an entire star. The principle does not act because particles recognize one another or consciously defend their space. It is built into the way identical fermions are described in nature. The stability of matter therefore depends not only on attraction and repulsion, but on a deeper refusal of certain particles to become completely indistinguishable in their state. What feels like the simple fact that one object cannot pass effortlessly through another is connected to a rule operating silently within every handful of matter you touch. Quantum physics determines the structure of every chemical element. The periodic table is not merely a catalogue invented to organize substances. It is a visible map of quantum architecture. Every chemical element is defined by the number of protons in its nucleus, but the character you encounter in chemistry emerges largely from the way its electrons arrange themselves around that nucleus. Quantum mechanics permits electrons to occupy specific families of states, each with particular energies, shapes, and capacities. As the number of protons increases from one element to the next, electrons fill these available states according to rules involving energy, spin, and exclusion. The repeating pattern of this filling creates the repeating structure of the periodic table. Elements placed in the same column often behave similarly because they possess comparable arrangements of outer electrons, the electrons most involved in chemical reactions. Sodium readily loses one outer electron, while chlorine tends to gain one, allowing them to form common salt. Noble gases are unusually unreactive because their outer quantum states form especially stable arrangements. Carbon can build an extraordinary variety of molecules because its outer electrons allow several strong bonds, making it central to the chemistry of life. The shapes of electron states also influence the angles at which atoms bond, helping determine whether molecules become straight, bent, flat, or three-dimensional. These shapes affect how medicines fit into biological receptors, how proteins fold, and how materials acquire their strength or flexibility. Even periodic trends such as atomic size, reactivity, and the energy needed to remove an electron arise from the balance between nuclear attraction, electron shielding, and quantum state filling. Chemistry is therefore not a separate layer of nature placed above physics by coincidence. It is what quantum rules look like when many electrons and nuclei build stable relationships. Every element has its personality because the same underlying laws produce a different electronic arrangement as nuclear charge changes. The periodic table may appear to be a grid of names and symbols, yet beneath it lies a deeper order. 90 naturally occurring variations on how matter can organize its electrons and, through that organization, create the material diversity of planets, oceans, atmospheres, and living bodies. The colors of objects begin with quantum energy transitions. Every color resting on the world around you begins with a decision made at a scale too small for your eyes to witness. When light reaches a material, its photons carry different amounts of energy, and the electrons inside atoms and molecules can absorb only those photons that match specific allowed transitions. The rejected wavelengths may be reflected, scattered, or transmitted, and this filtered light is what finally enters your eyes as color. A red apple does not contain redness as a substance hidden beneath its skin. Its pigments absorb much of the blue and green light falling upon them while returning more red light toward you. A green leaf appears green because chlorophyll strongly absorbs red and blue wavelengths for photosynthesis, but reflects more of the middle portion of visible light. In gases, isolated atoms often absorb or emit sharply defined colors because their energy states are relatively distinct. In liquids and solids, neighboring atoms, molecular vibrations, crystal structures, and electron bands broaden and reshape these responses, producing the rich colors of minerals, paints, metals, and living tissue. Some materials change color when heated because temperature alters which energy processes become available, while others glow under ultraviolet light after absorbing high-energy photons and releasing lower-energy ones later. Structural colors, such as the shifting blue of certain butterfly wings, involve microscopic patterns that redirect and interfere with light. Yet the material's quantum properties still help determine how strongly its electrons respond. Even gold's warm appearance begins with unusual electron behavior influenced by relativity, which changes which wavelengths it absorbs. What you call color is therefore not a permanent label attached to an object, but the result of an encounter between quantized light, the permitted energies of matter, and the biological machinery of your vision. The world outside you contains wavelengths and transitions. Your mind turns their selective arrival into blue oceans, green forests, and the red glow of evening, quietly converting quantum events into the emotional surface of reality. Lasers work by making atoms release matching photons. Laser begins when matter is persuaded to produce light with an order that ordinary lamps can rarely achieve. In a glowing bulb, excited atoms release photons at many different times, in many directions, and with phases that bear little relationship to one another, creating light that spreads and mixes freely. A laser works through stimulated emission, a process predicted by Einstein in which an incoming photon encounters an atom or molecule already holding extra energy and encourages it to release a second photon. The new photon matches the first in frequency, direction, polarization, and phase, allowing the two waves to reinforce one another instead of wandering apart. To make this multiplication continue, engineers create a population inversion, placing more particles in an excited condition than in the lower state they would normally prefer. This requires an external energy source, such as electricity, another light source, or a chemical reaction. The active material is positioned between mirrors, so photons travel back and forth through it, stimulating additional emissions on every pass. One mirror reflects nearly all the light, while the other allows a controlled portion to escape as the laser beam. Because the photons have been selected and amplified through the same process, the beam can be narrow, highly directional, and concentrated into a small area. Not every laser produces visible light, and not every beam is dangerously powerful. Lasers can operate in infrared, ultraviolet, microwave, and other regions, with designs ranging from tiny devices inside barcode scanners to immense systems used in precision research. Their ordered light allows surgeons to cut or reshape tissue, engineers to measure distance, fiber optic networks to carry information, and scientists to detect movements far smaller than a human hair. Yet a laser does not create perfect light from nothing. Energy must be supplied, some is lost as heat, and the exact output depends on the allowed transitions of the chosen material. Its beauty lies in coordination. Countless atoms, normally releasing light independently, are guided into contributing to one growing electromagnetic pattern. A laser is therefore a reminder that extraordinary precision can emerge when many microscopic events are not merely energetic, but synchronized. Modern electronics depend on the quantum behavior of electrons. Every digital image, recorded voice, and message moving across the world depends on devices built around places where electrons are allowed to move and places where they are not. Modern electronics became possible because electrons inside solids do not possess an unrestricted range of energies. In a crystal, the repeating arrangement of atoms transforms individual atomic states into broad energy bands separated by gaps. In conductors, electrons can readily enter nearby available states and respond to an electric field, allowing current to flow. In semiconductors, a modest energy gap normally limits that movement, but engineers can alter the material with extraordinary precision. By adding tiny amounts of selected impurities, a process called doping, they create regions with extra mobile electrons and regions that behave as though they contain positively charged vacancies called holes. Bringing these regions together forms junctions that can guide current in one preferred direction or control whether it flows at all. The transistor uses this controllability as an electronic switch. A small voltage changes the distribution of charge inside the device, opening or closing a channel through which current can pass. Billions of such switches can now be placed on a single chip, combining into circuits that calculate, store information, display images, and coordinate almost every modern machine. Quantum mechanics determines the band structure, the allowed electronic states, the response of materials to voltage, and the limits engineers face as transistors become smaller. At nanometer scales, electrons may leak through thin insulating barriers by tunneling, creating unwanted current and heat. Yet carefully controlled quantum effects can also be useful in flash memory, light-emitting diodes, solar cells, and specialized nanoscale devices. A computer does not normally perform quantum computation merely because its components obey quantum physics. Its bits still operate as stable classical zeros and ones, but the hardware beneath those bits could not exist without quantum laws. The screen in front of you may appear to be a world of symbols and software, yet every instruction ultimately becomes a controlled rearrangement of electrons inside engineered materials. Human thought is translated into voltage. Voltage reshapes quantum states, and those invisible changes return as language, music, maps, and memory. The digital world feels abstract, but its foundation is physical. An immense civilization built by learning how to guide electrons through landscapes that only quantum mechanics can describe. Quantum superposition means several outcomes can remain possible together. A quantum system can carry several mutually exclusive futures without choosing between them in advance. And the crucial mystery lies not merely in their coexistence, but in the way those possibilities remain able to influence one another. This condition is called superposition. It is often compared to a coin being both heads and tails. Yet that image is incomplete because an ordinary hidden coin already has one face upward, even when you have not looked. A true quantum superposition contains a structured combination of alternatives, including phase relationships, that determine how those alternatives later reinforce or cancel one another. An atom, for example, can be prepared in a combination of two energy states, and its later behavior depends on the precise relationship between them. Change that relationship, and the probabilities of future measurements change, even though the list of possible outcomes remains the same. Superposition is also dependent on which property you choose to examine. A state that gives one definite answer for one type of measurement may become a combination of possibilities when questioned in another way, much as a direction that looks simple from one viewpoint can require several components from another. This is why superposition should not be imagined as a collection of ordinary realities piled together like transparent photographs. It is a single quantum state with a richer internal structure than any one classical outcome. Engineers preserve and control this structure in atomic clocks, precision sensors, and quantum processors, where even tiny, unwanted interactions can disturb the delicate relationships between alternatives. When a definite result eventually appears, only one outcome enters the record, but the statistics of repeated experiments reveal that the other possibilities were not empty guesses. They helped shape which result became likely. Quantum superposition therefore teaches you that possibility can possess organization before certainty arrives. The future is not always a blank page containing several unrelated endings. At the quantum level, the possible endings can overlap, combine, and quietly alter one another before the world presents a single line for you to read. Wave function encodes the possible results of a quantum experiment. Behind every successful quantum prediction is an object you cannot photograph, hold, or place directly on a detector: the wave function. It is the mathematical description used to encode everything quantum theory allows you to predict about a prepared system. Depending on the experiment, it can represent possible positions, energies, spins, arrival times, or other measurable outcomes, assigning a special quantity called an amplitude to each alternative. The wave function is not simply a cloud showing where a particle is physically spread, nor is it an ordinary wave made from vibrating matter. In some cases, it can be displayed as a pattern across space, but for several particles, its full description exists in a more abstract space containing all their possible combined arrangements. This is one reason entangled systems cannot always be pictured as separate waves moving independently through three-dimensional space. The wave function also contains phase information, which allows alternatives to interfere. Two possibilities may each have large amplitudes and still cancel in a particular outcome because their phases oppose one another, while smaller contributions may combine and become important elsewhere. Between measurements, the wave function changes according to precise dynamical rules, allowing physicists to calculate how the landscape of possible results evolves over time. Yet the theory does not directly tell every interpretation what the wave function is. Some physicists regard it as a real feature of the world, others as a representation of available knowledge, and still others connect it to branching histories or deeper hidden structures. These views disagree about reality while using the same wave function to obtain the same experimental predictions. What is beyond dispute is its extraordinary usefulness. It guides the design of lasers, atoms, molecules, semiconductors, and quantum technologies with unmatched accuracy. The wave function is therefore less like a photograph of what exists and more like a complete grammar of what the system can reveal. It does not hand you one inevitable future. It preserves the structure of every permitted answer, how those answers relate, and how the question you eventually ask will transform that hidden structure into something a detector can record. The Born rule turns quantum possibilities into measurable probabilities. Quantum theory would remain a silent landscape of abstract possibilities, if one rule did not tell scientists how often each possibility should become an actual result? That bridge is the Born rule. The wave function assigns an amplitude to every allowed outcome, but an amplitude is not itself a probability. It can carry a phase and may even behave as though it has a positive or negative direction, allowing different alternatives to strengthen or cancel each other before measurement. To obtain the probability of a particular recorded result, physicists use the magnitude of its amplitude in a specific way, effectively removing the phase from that single outcome, while preserving the interference that occurred during the calculation. This conversion guarantees that probabilities are never negative, and that all mutually exclusive results add up to a complete set of possibilities. The distinction is essential. If probabilities were added directly from the beginning, quantum interference would vanish, and experiments would resemble ordinary random processes. Instead, amplitudes combine first, and probabilities appear only at the end. This is why two available routes can make a destination less likely rather than more likely. Their amplitudes can cancel even though either route alone would permit an arrival. The Born rule does not usually predict which detector will click in one individual trial. It predicts the distribution that emerges after the same preparation is repeated many times. A detector may appear unpredictable from event to event, yet thousands of results settle into proportions that match the rule with remarkable precision. Scientists have tested these predictions across atomic physics, optics, particle experiments, chemistry, and modern technology, finding no confirmed failure of the rule. And yet its deeper origin remains debated. Some interpretations accept it as a fundamental law, while others try to derive it from decision theory, symmetry, or the structure of quantum states. The rule works so well that civilization depends on it, but why nature converts amplitudes into probabilities in exactly this manner is still not fully explained. You are left with a profound contrast. Quantum mechanics tells you how possibility becomes statistically visible with extraordinary accuracy, while refusing to say why reality chose this particular arithmetic for turning what might happen into what eventually does. Quantum measurement produces one result from several possible outcomes. A detector never reports a cloud of half answers. It gives you one click, one flash, one number, and leaves the other possibilities unrecorded. This sharp transition is the heart of the quantum measurement problem. Before measurement, quantum theory may describe several outcomes as parts of one evolving state. But once the system interacts with a large apparatus, the result becomes amplified into something stable enough to enter the ordinary world. A microscopic event may free an electron, trigger an electrical pulse, illuminate a pixel, or move a pointer that millions of atoms help preserve. By the time you read the result, the fragile quantum event has become a durable fact. Standard textbook quantum mechanics represents this change with what is often called collapse. The state used to describe several possible answers is replaced by the state corresponding to the one answer obtained. Yet the theory does not fully explain what collapse physically is, when exactly it occurs, or whether it represents a real event rather than an update in description. Different interpretations offer different stories. Some treat collapse as fundamental, some say every possible result continues in separate branches, and others propose hidden processes beneath the visible statistics. All agree, however, on what the laboratory shows. Each individual measurement produces a definite record. You never see a measuring needle resting in several visibly different positions at once. The difficulty is that the equation describing an isolated quantum system allows combinations of outcomes to evolve smoothly, while experience presents only one completed result. Measurement, therefore, marks the border between two kinds of description: the open structure of what could be observed and the irreversible record of what was observed. The instrument does not merely reveal a miniature classical fact that was necessarily waiting in complete form. It participates in a physical chain that turns a microscopic possibility into a macroscopic event. And when that chain ends with a single mark on a screen, quantum physics can predict the pattern of such marks with astonishing accuracy, while still leaving you with the oldest unanswered question in the theory: why this result, in this moment, became the one reality you were allowed to witness. Decoherence makes quantum possibilities look like ordinary reality. The everyday world appears definite because delicate quantum relationships are being scattered into places you can no longer follow. This process is called decoherence, and it begins whenever a quantum system becomes entangled with many uncontrolled parts of its surroundings. Imagine a tiny object prepared so that two distinguishable conditions remain capable of interfering. A stray photon reflects from it, an air molecule collides with it, or vibrations inside the apparatus carry away a faint trace of its condition. After enough such interactions, the information that once linked the alternatives is no longer contained in the object alone. It has spread into an enormous web involving the environment. The alternatives have not necessarily been destroyed in the equations, but their phase relationship has become inaccessible to any realistic experiment, so interference between them effectively disappears. This is why a grain of dust does not display an obvious combination of being in two distant places. Light, heat, air, and internal motion reveal its position to the surroundings almost instantly, dispersing the coherence required for the alternatives to behave as one unified quantum state. Decoherence also explains why certain stable properties, such as approximate position, dominate the world you experience. The environment repeatedly preserves some kinds of information while rapidly erasing observable signs of others, selecting what physicists call robust or pointer-like states. Yet decoherence must not be given more credit than it deserves. It explains why different alternatives stop interfering and why a quantum system begins to look like a classical statistical mixture. But it does not by itself explain why you experience one unique outcome rather than the entire combined state. That remaining issue depends on how quantum mechanics is interpreted. Still, decoherence solves an enormous part of the puzzle by showing that the classical world does not require quantum laws to switch off at a mysterious size. Ordinary reality emerges because large systems cannot remain isolated from the countless interactions surrounding them. The familiar world is not non-quantum beneath its surface. It is quantum reality whose most delicate connections have leaked beyond practical recovery, leaving behind the stable, separated possibilities your senses mistake for the only forms that were ever present. The environment is constantly measuring quantum systems. Long before a scientist places a detector beside a particle, the surrounding universe has already begun collecting traces of what that particle is doing. Every collision with an air molecule, every exchange of heat, and every photon that scatters from an object can carry information away into the environment. These interactions act like countless incomplete measurements, not because the environment is conscious, but because different conditions of the system leave different physical marks around them. A sunlit object constantly sends reflected photons outward, and each photon may contain information about its location, shape, or motion. You see the object because a tiny fraction of those records reaches your eyes, while countless others spread through the room. In this sense, the environment does more than disturb quantum systems. It continuously monitors certain features and distributes copies of that information through many channels. A concept known as quantum Darwinism explores how some states become effectively objective because information about them is redundantly recorded in the surroundings. Several observers can examine different fragments of the environment and agree that a table occupies one position without directly interacting with every atom in the table. They are sampling separate copies of the same stable information carried by reflected light. Fragile properties that do not survive this environmental monitoring disappear from practical view, while robust properties are repeatedly reinforced. This helps explain why the world seems public and shared rather than private and quantum mechanical. Isolation is therefore one of the hardest challenges in quantum experiments. Researchers cool systems, remove air, block stray radiation, suspend objects, and shield them from electrical and magnetic noise, all to prevent the outside world from learning too much too quickly. Even then, Internal vibrations or tiny imperfections can reveal unwanted information and destroy the behavior scientists are trying to preserve. The environment is not a silent background surrounding the experiment. It is an active network of interactions that is always asking physical questions and carrying partial answers away. What you call an ordinary object is partly an object whose condition has been announced so many times to its surroundings that disagreement becomes nearly impossible. Reality feels definite not only because things possess stable features, but because the universe is constantly repeating those features back to itself. Large objects lose visible quantum behavior extremely quickly. Place a dust grain in a quantum superposition, and the universe will begin erasing the evidence before you could finish blinking. The difficulty is not that large objects suddenly stop obeying quantum mechanics, but that they contain enormous numbers of particles, internal vibrations, rotating molecules, moving electrons, and thermal motions, all capable of becoming linked with the object's wider condition. A single atom can sometimes be isolated well enough for two alternatives to remain coherent, but a visible object offers countless routes through which information can escape. Heat radiated from its surface can reveal something about its position. Air molecules can strike different regions and carry away distinct traces. Light can scatter from it in slightly different directions. Even interactions occurring entirely inside the object can distribute information among its own components, making the original quantum relationship nearly impossible to reconstruct. Size matters partly because larger objects present a bigger target to their surroundings, but complexity and temperature are equally important. A cold, carefully suspended mechanical resonator may preserve quantum behavior longer than a much smaller object vibrating chaotically in a warm room. This is why laboratories use extreme vacuum chambers, shielding, precise cooling, and carefully chosen materials when they try to observe quantum states in increasingly massive systems. The challenge grows brutally fast. For a microscopic particle, one unwanted collision may be rare. For a grain of dust, collisions, photons, and internal disturbances arrive in overwhelming numbers, causing visible interference to vanish on timescales far shorter than human perception. Yet nothing magical occurs when the object becomes large. The underlying quantum description remains, but its fragile alternatives become spread across so many degrees of freedom that bringing them back together would require controlling an almost unimaginable amount of information. The ordinary world therefore appears definite, not because quantum physics has failed, but because large objects are too connected, too warm, and too internally complicated to keep their hidden alternatives coordinated. What you experience as classical certainty may simply be quantum possibility, losing its privacy almost instantly. Quantum effects do not end at a precise boundary between small and large. There is no known line in nature where an object crosses a certain size and quantum physics quietly switches itself off. Textbooks often separate the microscopic quantum world from the macroscopic classical world because the distinction is useful, but it is not written into the fundamental equations as a sharp border. An electron is quantum, an atom is quantum, and a molecule made from many atoms is still governed by quantum rules. Add more particles, increase the temperature, or allow stronger interaction with the surroundings, and quantum behavior becomes harder to observe. But it does not disappear at one exact mass, length, or level of complexity. This gradual transition is why scientists speak of mesoscopic systems, objects that sit between the obviously microscopic and the comfortably ordinary. Superconducting circuits containing currents formed by vast numbers of electrons can be prepared in states with no simple classical equivalent. Tiny mechanical resonators can have their motion cooled close to its lowest quantum level. Clouds of atoms can behave collectively as one coherent matter wave. These experiments show that large and quantum are not opposites. The decisive question is whether the relevant quantum relationships can be created, protected, controlled, and measured before noise overwhelms them. Different properties of the same object may also cross into classical-looking behavior at different rates. Its center of mass might preserve coherence, while its internal vibrations behave thermally, or one electrical variable may remain quantum while countless other details become effectively ordinary. This makes the boundary less like a wall and more like fog. The farther you move into warm, complex, strongly interacting systems, the harder quantum features become to distinguish. Yet there is no precise step where nature changes its laws. Some proposed theories suggest that gravity or spontaneous collapse may eventually impose a genuine limit, but no such boundary has been conclusively observed. Experiments continue pushing toward heavier masses, longer times, and larger separations to discover whether standard quantum mechanics ever fails. Until that happens, the most careful conclusion is also the strangest. The table, the mountain, and your own body are not outside quantum physics. They are systems in which quantum behavior has become so thoroughly hidden beneath complexity that it appears to have become another kind of reality. Molecules containing thousands of atoms can display wave-like behavior. Molecule large enough to possess a complicated shape, thousands of internal vibrations, and a mass far beyond a simple atom can still pass through an experiment as though it were a spreading wave. Matter-wave interference was first associated with electrons and other tiny particles, but modern experiments have extended it to increasingly massive molecules, including structures built from hundreds and even thousands of atoms. Researchers create beams of these molecules, guide them through carefully designed gratings or standing waves of light, and record where they arrive. Each molecule lands as one complete object rather than breaking into pieces across the detector. Yet after many individual arrivals, the distribution forms an interference pattern that depends on the molecule's wave-like propagation. The challenge is extraordinary because a large molecule is not a silent point. It can rotate, vibrate, absorb radiation, emit thermal photons, collide with stray gas, or reveal its route through tiny interactions. Any of these processes may carry enough information to destroy the observable pattern. Scientists must therefore send the molecules through high vacuum, control their temperature, limit outside radiation, and design gratings that do not accidentally measure which route was taken. The resulting interference does not mean the molecule becomes a soft material wave spread visibly through the laboratory. Its center of mass motion is described by a quantum state capable of following alternatives that later combine, while the molecule's internal structure remains intact. This distinction allows something chemically complex to display a simple quantum signature without behaving like one featureless particle in every respect. Such experiments are more than demonstrations of technical skill. They test whether quantum theory continues to work as mass and complexity increase. And so far, they have found no clear size at which matter waves suddenly fail. They also offer sensitive ways to search for unknown mechanisms that might cause large superpositions to collapse on their own. The deeper surprise is not merely that a large molecule can act like a wave. It is that complexity does not automatically erase quantum nature. Given enough isolation and control, an object with many thousands of moving parts can still reveal that its journey was shaped by alternatives no classical path could reproduce, as though the familiar solidity of matter were only the final surface of a much quieter wave beneath. Scientists have placed tiny mechanical objects into quantum states. A device you could almost imagine hearing vibrate has been made to move according to rules once associated only with atoms. Scientists have built microscopic mechanical resonators, tiny beams, membranes, and drum-like structures containing enormous numbers of atoms, then cooled selected modes of their motion until nearly all ordinary thermal vibration disappeared. The object itself does not become perfectly motionless, because quantum mechanics still permits a lowest possible level of motion known as the ground state. In a landmark experiment, researchers created a mechanical resonator on a chip, cooled one of its vibration modes close to that ground state, and coupled it to a superconducting quantum bit. The qubit allowed them to add and remove individual packets of vibrational energy called phonons, giving them control over the motion one quantum at a time. This was not simply an atom behaving quantum mechanically inside a machine. The measured vibration belonged to a manufactured mechanical structure involving the coordinated motion of vast numbers of atoms. Later experiments used light and radiation pressure to cool other resonators toward their quantum ground states, turning mechanical motion into something that could exchange information with photons, electrical circuits, and qubits. Yet the phrase, "a mechanical object in a quantum state," must be understood carefully. It does not necessarily mean that the entire device has been placed in two visibly separated locations, nor that you could look at it and see contradictory shapes. Usually, scientists control one particular mode of vibration, while many other properties of the object remain ordinary and warm. The achievement lies in isolating a collective movement well enough that its energy arrives in discrete steps and cannot be explained as classical shaking. These systems may one day connect different parts of quantum technologies, convert information between microwave and optical signals, and measure extraordinarily weak forces. More quietly, they test how far quantum principles can be extended into the world of constructed objects. A mechanical resonator is designed in a laboratory, etched from solid material, connected to wires, and large enough to contain more atoms than you could ever count. Yet one chosen motion within it can still behave like a single quantum oscillator. The boundary between machine and quantum system is therefore not a boundary of material, but of control. When heat and noise are stripped away with enough precision, even a tiny engineered drum can reveal that motion itself comes in indivisible steps, as though the solid world has been carrying a hidden rhythm beneath every vibration you have ever felt. Atoms can be cooled until they behave like one collective quantum wave. Lower the temperature of a gas far enough, and thousands or millions of separate atoms can lose the ordinary distinction between one atom's motion and another's. At room temperature, atoms rush through space with many different speeds and directions, colliding chaotically and carrying matter waves so short that their quantum identities remain effectively separate. Scientists begin taming this motion with laser cooling. Carefully tuned beams of light are arranged so that atoms moving toward a beam are more likely to absorb photons opposing their motion, gradually reducing their speed. Magnetic fields and additional lasers can then confine the slowed atoms inside a trap without placing them in a physical container whose walls would warm them. Laser cooling alone is often not enough, so researchers use evaporative cooling, allowing the fastest atoms to escape while the remaining atoms collide and redistribute their energy at a lower temperature. This resembles steam carrying energy away from a hot liquid, except the process occurs in a gas held by electromagnetic fields and can bring temperatures to a tiny fraction above absolute zero. As the atoms slow, their matter wavelengths become longer. Eventually, those wavelengths overlap so strongly that assigning a separate wave to each atom no longer captures the system's behavior. For particles known as bosons, a large fraction can then gather into the same lowest energy quantum state. The collection begins acting like one coherent matter wave, sharing a common phase across distances far larger than an individual atom. The atoms do not physically fuse, lose their nuclei, or become one giant particle. A detector can still count separate atoms after the cloud is released. What becomes collective is their quantum description and the coordinated way their motion evolves. This transformation was first achieved in dilute atomic gases in 1995, when researchers cooled rubidium atoms until a sharply concentrated population appeared in the lowest state. The result created a new form of matter under laboratory control, and demonstrated that wave-like behavior could organize an entire atomic cloud. Cooling here is not merely the removal of warmth, it is the gradual silencing of individual motion until a deeper order becomes audible. When the thermal noise fades, atoms that once rushed independently can begin responding as parts of one extended quantum object, suggesting that individuality in matter may depend partly on how loudly heat is shaking its pieces apart. Bose-Einstein condensates make quantum behavior visible on larger scales. Release 2. Bose-Einstein condensates and let them overlap, and the expanding clouds can paint broad stripes of matter across a detector, making the wave nature of atoms visible without requiring you to inspect a single atom. A Bose-Einstein condensate, often shortened to BEC, forms when many bosonic particles occupy the same quantum state and behave as one coherent matter wave. Its importance is not simply that it is extremely cold. Many things can be cold without becoming condensates. What makes a BEC extraordinary is the large-scale order shared across the cloud. The atoms possess a collective phase, allowing different parts of the condensate to combine in predictable ways. When two condensates overlap, their matter waves can reinforce one another in some regions and cancel in others, producing interference fringes similar in principle to overlapping light waves. Each detected atom still arrives as an individual event, but the complete pattern reveals an organized wave extending across the whole sample. Condensates can also flow in ways that resemble superfluids, moving with dramatically reduced internal friction under suitable conditions. Stir one carefully, and instead of rotating like water in a bucket, it can form quantized vortices, tiny whirlpools whose circulation is restricted to specific allowed amounts. Researchers can confine condensates in ring-shaped traps, split and recombine them for precision measurements, guide them through atom interferometers, and release narrow streams of coherent atoms in devices sometimes called atom lasers. The name does not mean the atoms become light. It means the emitted matter shares an order somewhat analogous to the coordinated photons in an optical laser. Because a BEC responds collectively, it can make subtle quantum effects easier to observe and control across distances much larger than individual atomic dimensions. It has become a laboratory for studying superfluidity, vortices, waves, phase transitions, and simplified models of complex materials. Yet a condensate is not a single frozen lump detached from ordinary physics. Interactions between atoms still matter. Imperfections can create excitations, and heating eventually destroys the shared order. Its large-scale quantum appearance must be continually protected and prepared. Even so, a BEC offers something rare, not merely evidence that microscopic particles obey strange rules, but a visible consequence of many particles obeying one rule together. It allows you to watch a cloud expand, divide, flow, and interfere as though matter has remembered that it was always capable of behaving like a wave. In that quiet cloud, quantum mechanics no longer feels hidden beneath the surface of the world. It rises into a form large enough to image, shape, and guide, giving you a glimpse of what matter can become when millions of separate motions settle into one shared rhythm. Fermions and bosons obey completely different quantum rules. Every known quantum particle belongs to one of two great families, and the universe would become almost unrecognizable if their rules were exchanged. These families are called fermions and bosons, distinguished by a quantum property known as spin, although spin is not ordinary physical rotation. Fermions include electrons, quarks, neutrinos, protons, and neutrons, while bosons include photons, gluons, and the particles associated with several fundamental forces. Their deepest difference appears when two identical particles are exchanged in a quantum description. For bosons, the combined state keeps the same form, allowing them to reinforce one another and gather into shared conditions. For fermions, the state changes sign, creating a structure that forbids two identical fermions from having every quantum property in common. This difference may sound abstract, yet it separates much of what you call matter from much of what carries interactions. Fermions build layered structures because they must spread across available states, while bosons can accumulate and act collectively. The distinction is not simply matter particles versus force particles, because composite objects can change category. A proton is made from 3 quarks and behaves as a fermion. Some atoms containing an even total number of fermionic components can behave as bosons, while others with an odd total behave as fermions. What matters is the overall quantum spin of the complete object. This classification influences how gases cool, how stars resist compression, how light accumulates in radiation fields, and why certain materials can enter extraordinary collective phases. It even shapes the statistical laws used to predict how particles distribute themselves across available energies. Fermions follow Fermi-Dirac statistics, while bosons follow Bose-Einstein statistics, two different forms of quantum bookkeeping with consequences stretching from laboratory traps to the interiors of stars. Nature, therefore, does not use one universal rule for every identical particle. It divides them into two types, whose opposite responses to sameness help organize the physical world. The objects around you exist not only because particles have mass and charge, but because some particles refuse complete sameness while others readily embrace it, turning a quiet distinction in quantum symmetry into the architecture of matter and radiation. Bosons can gather into the same quantum state. Give one boson a place to settle, and the arrival of others can make that same destination more attractive rather than more crowded. Unlike fermions, identical bosons are permitted to occupy precisely the same quantum state, sharing the same energy, motion, and other relevant properties without violating any exclusion rule. More remarkably, quantum statistics can make a transition into an already occupied state more likely than a transition into an empty equivalent state. This tendency is sometimes called bosonic enhancement or stimulated occupation. It does not mean bosons feel an ordinary attractive force pulling them together. The effect arises from the symmetry of their shared quantum state, which makes histories involving indistinguishable bosons combine in a way that favors collective occupation. Photons reveal this behavior naturally because many photons can possess the same frequency, direction, and polarization. Their ability to accumulate in matching modes helps explain the intense collective behavior of radiation, though the engineering of lasers adds carefully prepared atoms and stimulated emission to control that process. Bosonic gathering also appears in liquid helium-4, whose atoms behave as composite bosons. At low temperatures, a large fraction of the liquid participates in a shared quantum condition, contributing to superfluid behavior, such as flow through narrow channels, with remarkably little resistance. Other bosonic systems can create coherent waves, quantized vortices, and collective excitations that act more like the motion of one organized whole than the random movement of separate particles. Yet bosons do not always collapse automatically into one state. Temperature, density, interactions, trapping conditions, and whether particle number is conserved all affect what happens. A warm gas of bosonic atoms may still behave almost classically because thermal motion spreads them across many states. Strong interactions can also complicate the simple picture and produce new phases. The important point is not that bosons always crowd together, but that quantum mechanics places no fundamental occupancy limit on them. The presence of one does not close the door to another. In the correct conditions, the door can become easier to enter. This gives bosons a natural capacity for coordination, allowing many separate quanta to contribute to one amplified pattern. Their individuality does not vanish, yet the system can become dominated by a shared state so strongly that the collective behavior is more visible than the particles composing it. Bosons show you a side of nature in which sameness is not a restriction, but a pathway toward order. Fermions resist, occupying the same quantum state. Crowd identical fermions together, and they respond not by forming one shared condition, but by filling an invisible ladder of increasingly different states. This resistance is not caused by electrical repulsion, and remains present even for neutral fermions that exert little ordinary force on one another. It emerges from the antisymmetric structure required of their combined quantum state. If two identical fermions were assigned exactly the same set of quantum properties, the mathematical description would cancel itself, leaving zero probability for that arrangement. As a result, adding fermions to a confined system forces newcomers into states that differ in energy, momentum, position pattern, or spin orientation. In a metal, this creates a vast Fermi sea of electron states filled up to a characteristic level known as the Fermi energy. even when the material is not especially cold by everyday standards. Most lower electronic states are already occupied, so many electrons cannot simply lose small amounts of energy and settle downward. Only electrons near the upper edge of the occupied distribution have nearby empty states available and can respond efficiently to heat or an applied voltage. This helps explain why the thermal and electrical behavior of metals differs so strongly from what a simple gas of charged particles would predict. It also means that cooling a fermionic system does not cause every particle to gather into one lowest state. Instead, the particles form a structured distribution with quantum pressure and collective properties surviving even when ordinary thermal motion becomes small. In ultra-cold laboratories, scientists trap fermionic atoms and observe a sharply defined Fermi surface, pair formation, and transitions into states that resemble superconductivity. Under suitable attraction, two fermions can join as a pair whose combined behavior is bosonic, allowing collective order to emerge without either fermion abandoning its own statistical nature. This pairing lies behind conventional superconductivity, where electrons coordinate through Cooper pairs rather than all occupying one identical single electron state. Fermionic resistance to sameness is therefore not merely a rule that keeps particles apart. It determines which particles can change energy, which can carry current, how cold matter stores motion, and when pairing becomes advantageous. Beneath the apparent calm of a solid object lies a densely filled landscape in which countless fermions continually respect one another's occupied states. Their refusal to become perfect copies does not create disorder. It creates structure, turning limitation into one of nature's most powerful sources of organization. The difference between fermions and bosons shapes the material universe. Change the quantum identity of nature's particles, and the universe would not merely look different. It might lose the ability to build stars, chemistry, and stable objects altogether. Fermions and bosons do more than follow separate statistical rules. Together, they divide physical reality into two complementary forms of behavior. Fermions create resistance to unlimited crowding, forcing matter into layered structures with distinct energies, while bosons allow coordinated collective effects and help carry the interactions through which particles influence one another. This division reaches far beyond the scale of laboratories. Inside ordinary matter, fermionic electrons arrange themselves around atomic nuclei in ways that create chemical shells, bonding patterns, and the repeating order of the periodic table. Inside atomic nuclei, fermionic protons and neutrons fill their own available states, helping determine which nuclei are stable and which eventually decay. In stars, the statistical pressure produced by crowded fermions can resist gravitational compression long after ordinary thermal support weakens, shaping the existence of white dwarfs and neutron stars. Bosons play a different role. Photons carry electromagnetic energy. Gluons bind quarks inside protons and neutrons, and the particles associated with the weak interaction allow certain forms of radioactive transformation. Even the Higgs boson is linked to the field through which many elementary particles acquire mass. This familiar separation is not perfectly captured by saying fermions are matter and bosons are forces, because composite particles can behave as either family depending on their total spin, and some bosons can form material systems of their own. The deeper distinction is one of symmetry. Exchange two identical particles, and the combined quantum description responds in one of two fundamentally different ways. From that quiet mathematical difference emerge atomic size, stellar stability, radiation, nuclear binding, and the large-scale texture of the cosmos. The universe is therefore shaped not only by what particles weigh or how strongly they attract, but by how nature treats sameness itself. Some particles construct complexity by refusing to occupy one condition together. Others create coherence by sharing it. Between those two tendencies, matter gains structure and energy gains pathways, allowing a universe that is neither a featureless collapse nor a shapeless flood. but a place where separation and cooperation remain balanced closely enough for stars to burn and for you to exist beneath them. Every electron in the universe has exactly the same fundamental properties. An electron formed in the early universe is indistinguishable from one released inside a device on Earth today, as though nature has been producing the same particle from a single perfect template for billions of years. Every electron carries the same negative electric charge, the same rest mass, the same spin, and the same magnetic behavior within the extraordinary precision of modern experiments. There are no heavier electrons hidden in distant galaxies, no younger electrons with slightly different charges, and no visible markings that reveal where an electron was created or what it experienced before reaching a detector. This sameness is far more exact than the resemblance between manufactured objects. Two machines built from the same design always contain tiny imperfections, but electrons do not appear to be separate products assembled with varying quality. In quantum field theory, this becomes easier to understand because an electron is treated as an excitation of one universal electron field. The same field exists everywhere, so every electron is not an independently manufactured object, but another occurrence of the same fundamental pattern. This uniformity is essential to the stability of physics. If electrons differed even slightly from place to place, atoms of the same element would not behave consistently. Chemical reactions could change across the universe, and light from distant stars would reveal shifting atomic signatures. Instead, astronomers observe the same recognizable spectral patterns across enormous cosmic distances, showing that the basic properties governing electrons have remained remarkably consistent. The identity of electrons also creates unusual consequences when several occupy the same system, because no experiment can label one electron as the original and another as the replacement. Exchanging them cannot produce a separately observable history. An electron captured by an atom may later be emitted, yet asking whether it is the same electron in the everyday personal sense may not correspond to a physical distinction nature preserves. What continues is the excitation and its conserved properties, not a private biography attached to a tiny object. This does not make electrons unreal or interchangeable in the careless sense that their locations never matter. Detectors register individual events, and electrons can occupy very different states, but their fundamental identity remains exact. At the deepest level, nature appears capable of repeating a pattern without variation, suggesting that the universe is not built from countless individually crafted pieces, but from a limited set of perfect physical forms appearing again and again wherever the fields of reality are disturbed in the right way. An electron has no known internal structure. Probe an electron with the most powerful experiments humanity can build, and it still refuses to reveal any smaller machinery inside itself. Protons and neutrons once appeared elementary, but high-energy scattering eventually showed that they contain quarks and gluons. The electron has not followed the same story. In the standard model of particle physics, it is treated as an elementary particle, meaning that it is not currently understood as a bound collection of smaller components. When electrons are scattered at extremely high energies, they behave as point-like objects down to distances far smaller than an atomic nucleus. This does not mean physicists have proved that an electron is a literal mathematical point with absolutely no internal structure at every conceivable scale. It means no experiment has detected a measurable size, internal parts, excited substructure, or variations suggesting that the electron is composite. If it contains smaller charged pieces, collisions might reveal unexpected patterns, energy-dependent shapes, or new excited versions of the electron. Precision measurements of its magnetic properties could also deviate from the predictions of quantum electrodynamics. So far, the agreement between theory and experiment is astonishingly close, leaving very little room for hidden internal architecture. The electron still possesses properties that may sound as though they require a tiny physical surface, such as charge, spin, and a magnetic moment. But quantum physics does not need to explain these by imagining a rotating ball with charge painted across it. They are intrinsic properties of the electron's quantum state. This is one reason visual intuition becomes unreliable. A point-like particle can carry angular momentum without spinning like a wheel, interact through fields without having a solid boundary, and produce measurable effects without containing visible internal parts. Some speculative theories propose that electrons could be strings, composite objects, or emergent excitations of deeper structures. But none has yet produced confirmed evidence that replaces the elementary particle description. The honest scientific position is therefore both powerful and incomplete. The electron behaves as though it has no internal structure, but experiments can only test down to finite scales. Each improvement in energy and precision pushes the search deeper, asking whether simplicity is fundamental or merely the next layer of concealment. For now, one of the most important building blocks of every atom remains strangely featureless. It carries charge, mass, spin, and a precise relationship with the fields around it. Yet when you ask what it is made of, nature offers no smaller object in reply. The electron may not be a container holding hidden pieces at all. It may be one of the places where the question, "what is inside?" finally stops making sense. Quantum spin is not ordinary rotation. The word spin invites you to picture a tiny sphere turning rapidly in the dark. But that familiar image leads almost immediately in the wrong direction. In quantum physics, spin is an intrinsic form of angular momentum, a built-in property that particles possess even when there is no meaningful surface, axis, or internal machinery that could physically rotate. Electrons respond to magnetic fields as if they carry a tiny magnetic orientation, and their spin contributes to the way atoms, materials, and particles behave. Yet this does not require the electron to be a miniature planet spinning around itself. The name survived because the measured effects resemble some consequences of rotation in classical physics, especially angular momentum and magnetism. But the similarity is mathematical rather than mechanical. Quantum spin follows transformation rules that ordinary rotating objects never obey. Turn a classical arrow through a full rotation and it returns to its original appearance. But the quantum description of a spin-half particle changes in a subtler way and requires 2 complete rotations to return fully to its starting form. This strange behavior is not something you can reproduce by painting a dot on a ball and spinning it. It belongs to the geometry of quantum states and to how particles respond when space is rotated around them. Spin also affects which combinations of particles are allowed, how atomic energy levels divide in magnetic fields, and why materials can become magnetic. In iron, for example, interactions between many electron spins can encourage large groups to align, creating a magnetic domain whose influence becomes visible at human scales. Yet an individual spin is not a tiny compass needle secretly pointing in an ordinary direction before every measurement. Its possible outcomes and later behavior depend on the orientation along which it is examined. The safest way to understand spin is therefore not to ask what little object is turning, but to ask how a quantum system responds to rotations and magnetic interactions. Nature has given particles a form of angular character without giving them the mechanical bodies your imagination expects. Spin is one of those moments when a familiar word survives only as a bridge, carrying you toward a property that belongs to reality, but not to any simple picture. Reality has taught you to trust. Particles can have spin without being tiny, spinning balls. If an electron were truly a small charged ball, rotating fast enough to produce its measured magnetism, parts of its imagined surface would face an impossible demand. Early attempts to interpret spin mechanically suggested that the electron might physically turn like a miniature globe, with its charge circulating and creating a magnetic effect. But the electron's observed properties cannot be explained consistently by such a model, because experiments place extremely strict limits on its size. A surface small enough to fit those limits would need to move faster than light to generate the required angular momentum through ordinary rotation. Relativity forbids that, and no hidden rigid sphere has ever been detected. The mechanical picture fails not because the particle spins too quickly, but because quantum spin was never the rotation of material parts in the first place. A fundamental particle can possess angular momentum in the same way it possesses electric charge, as an intrinsic property written into the rules governing its state. Charge does not require you to imagine smaller charged pieces glued inside the electron, and spin does not require a surface sweeping through space. This becomes clearer when you consider particles such as photons. Light carries spin and can transfer angular momentum to matter, causing tiny objects to rotate or influencing atomic transitions, even though a photon is not a solid bead turning as it flies. The property is revealed through interactions. It affects polarization, magnetic response, collision outcomes, and the conservation of angular momentum, all without providing a classical mechanism beneath them. Quantum field theory describes a particle as an excitation whose spin determines how it transforms under rotations and which interactions it can participate in. That description may feel abstract, but it predicts laboratory results more accurately than any miniature machine story. Human intuition evolved among stones, tools, wheels, and moving bodies, so it naturally demands that angular momentum must come from something physically circling. Quantum physics refuses that demand. It shows that some properties need no hidden gears to produce real consequences. A particle can exchange angular momentum, influence magnetism, and obey precise rotational rules while containing no known spinning material at all. The discomfort you feel is not evidence that the theory lacks meaning. It may simply reveal that reality is not obligated to build its smallest features from scaled-down versions of the objects you already understand. Spin measurements. Produce only certain allowed results. Aim a spin measuring device in any chosen direction, and a quantum particle will not return an arbitrary value from a smooth range of possibilities. For an electron, the result along that direction always belongs to one of two permitted outcomes, commonly described as spin up or spin down. The labels do not mean the electron is literally rotating clockwise or counterclockwise, nor do they identify a permanent top and bottom attached to the particle. They describe the two discrete answers the electron can give when its spin is measured relative to the selected axis. You may rotate the measuring apparatus by a small amount, yet the detector still does not report a slightly tilted fraction between the two results. It records one allowed value or the other. What changes with the apparatus's orientation is the probability of receiving each answer. A particle prepared to give a definite result along one direction can produce uncertain outcomes when measured along another, and the chances vary smoothly, even though the recorded answers remain sharply quantized. This separation between continuous experimental choices and discrete outcomes is one of spin's most revealing features. The measurement direction can point anywhere in space, but the result arrives in limited steps rather than as a classical projection of a hidden arrow. After the measurement, the particle is prepared in the state associated with the result obtained, so repeating the same measurement immediately will normally return the same answer. Change the direction of the apparatus, however, and the earlier certainty no longer provides a complete prediction. Spin measurements therefore reveal both order and limitation. Nature restricts which values can appear, while refusing to assign one fixed classical orientation that explains every possible test at once. This quantization is not a defect caused by insensitive equipment. More precise instruments sharpen the same allowed outcomes rather than filling the gaps between them. Similar rules apply to other particles, though the number of permitted results depends on the kind of spin they possess. Spin 1 particles, for instance, can yield 3 allowed projections along a chosen direction. The broader lesson is that some physical quantities are not continuous reservoirs from which nature selects any value it likes. They arrive in structured alternatives. You may freely choose the question's direction, but nature limits the vocabulary of its reply, offering certainty in distinct words, while leaving the sentence they form dependent on how you decided to ask. Measuring spin along one direction changes what can be known in another. Particle can answer one spin question with perfect certainty, and then lose that certainty simply because you ask a different question in between. Imagine preparing an electron so that a measurement along the vertical direction always gives the same result. If you immediately repeat that vertical measurement, the answer remains stable. But now turn the apparatus sideways and measure the spin along a horizontal direction. The electron must give one of the two allowed horizontal results, and that measurement prepares it according to the new direction. When you turn back and ask the original vertical question again, the outcome is no longer guaranteed. The earlier certainty has been replaced by fresh probabilities. This does not happen because the apparatus accidentally shakes the electron, or because the first result was poorly recorded. Spin components along different directions are incompatible quantum properties. A state that is definite relative to one axis is generally a structured combination of possibilities relative to another. Measuring the second direction does not uncover another part of a complete three-dimensional arrow hidden inside the particle. It changes the state into one suited to the new question, so information associated with the earlier direction can no longer remain fully sharp. The effect becomes especially clear in sequences of carefully aligned spin filters. A beam selected to contain only one vertical result can be split again by a horizontal filter. And after that horizontal selection, a final vertical filter produces both vertical outcomes. The middle measurement has restored an alternative that the first filter had removed. Nothing traveled backward, and no human awareness caused the change. The apparatus physically coupled to the particle and created a new quantum condition. This teaches a lesson more precise than saying measurement merely disturbs what exists. Different spin directions do not behave like separate pages of a book that can all be read without consequence. They are different ways of organizing the possible answers, and choosing one organization limits what can remain definite in another. You are free to rotate the question through space, but the particle does not carry a complete classical reply for every direction at once. Quantum knowledge is therefore shaped by sequence. What you can predict now depends not only on how the particle was prepared, but on which question the world was most recently forced to answer. The Stern-Gerlach experiment revealed the quantized nature of spin. A beam of silver atoms entered a magnetic field in 1922 and emerged divided into two distinct streams, leaving behind one of the clearest signs that nature does not always permit continuous answers. Otto Stern and Walter Gerlach designed the experiment to test how atomic magnetic moments orient themselves in a non-uniform magnetic field. A tiny magnetic object entering such a field experiences a force whose direction depends on its orientation. If each atom behaved like a classical magnet able to point at any angle, the beam should have spread into a continuous band on the collecting plate, with atoms deflected by every amount between the two extremes. Instead, the silver beam split into two separated traces. The atoms behaved as though only two orientations relative to the measuring direction were permitted. At the time, electron spin had not yet been introduced, so the original interpretation focused on what was called space quantization. Later understanding showed why silver was such a fortunate choice. Most of the electrons in a silver atom are paired in ways that cancel their magnetic contributions, leaving one unpaired electron to dominate the atom's response. The experiment therefore became a practical window into the two-valued spin behavior associated with that electron. Its significance was not that scientists had found two fixed directions built permanently into space. Rotate the magnet and the splitting follows the new axis chosen by the apparatus. The experiment reveals discrete projections relative to the selected direction, not tiny compass needles forever labeled up and down. The apparatus itself was also remarkable for its time, producing a narrow atomic beam, maintaining a vacuum, and shaping a magnetic field with a steep gradient required delicate engineering. The resulting silver deposit was so faint that historical accounts describe the trace becoming more visible through chemical effects associated with Stern's cigar smoke, though the scientific result did not depend on that dramatic detail. What mattered was the unmistakable absence of the classical smear. Stern and Gerlach had asked nature for a range and received 2 marks. That simple split helped open the modern understanding of spin, atomic magnetism, and quantum measurement. It showed that quantization was not confined to atomic energies or emitted light. Even the orientation-like properties of matter could arrive in distinct outcomes, as though the microscopic world speaks not in every possible shade, but in carefully restricted answers that become visible only when the right question is built into the laboratory. Quantum uncertainty is a property of nature rather than faulty equipment. Even a perfect instrument cannot reveal a quantum particle with every classical property sharpened at once, because the uncertainty is not merely hiding inside the machine. In ordinary experiments, uncertainty often means ignorance. A ruler has limited markings, a camera has blurred pixels, or a moving object changes before the observer reacts. Better tools can reduce these errors. Quantum uncertainty is different. Consider position and momentum. You can prepare a particle so that its location is confined to a very narrow region, but that localized state must contain a wide range of possible momenta. Prepare it with a sharply defined momentum, and its position becomes widely spread. This relationship arises from the wave structure of quantum states. A wave with one clean wavelength extends broadly through space, while building a narrow wave packet requires combining many wavelengths, each corresponding to a different momentum. The trade-off is therefore woven into the description itself. It is not necessary for a detector to strike the particle violently before uncertainty appears. The state can already lack simultaneous sharp values before any measurement is performed. Measurement disturbance can add further complications, but it is not the full origin of the principle. Scientists confirm this by preparing large collections of identical systems and examining the statistical spread of results. No matter how carefully the preparation is improved, narrowing one distribution forces the related distribution to broaden in the way quantum theory predicts. Similar limits exist for other pairs of incompatible quantities, though the details depend on the system. This does not mean everything in quantum physics is vague or that all properties are unknowable. A chosen quantity can sometimes be prepared and measured with extraordinary precision. The restriction concerns particular combinations of questions that cannot both possess unlimited sharpness in the same state. Nor does uncertainty mean that a particle must secretly have exact classical values that humanity is simply forbidden to discover. Some interpretations search for deeper variables, but experiments have ruled out many simple classical explanations. And standard quantum mechanics treats the spread as a genuine feature of the physical state. The principle is therefore not a confession of technological weakness. It is a statement about how nature organizes information. The world does not always contain a perfectly detailed classical picture waiting behind a curtain. At its foundations, precision has a shape. Sharpen one edge of reality, and another must soften, not because your hands are unsteady, but because the object you are trying to hold was never built with every edge sharp at once. Position and momentum cannot both be precisely defined at the same time. Try to trap a quantum particle inside an ever smaller region of space, and its future motion becomes increasingly difficult to describe with a single precise momentum. This is the position momentum uncertainty principle, one of the most important limits in quantum mechanics, but it is often misunderstood as a simple problem caused by measurement. It is true that observing a particle can disturb it, yet the deeper limitation exists even before a detector is switched on. A quantum state sharply concentrated around one location must be built from many different matter wave components, and those components correspond to a broad range of possible momenta. A state with one very precise momentum behaves in the opposite way. Its wave pattern extends across a large region, so it cannot also identify one sharply defined position. The two kinds of precision are linked by the structure of quantum states themselves. You can reduce one uncertainty, but doing so necessarily enlarges the other. This does not mean the particle has no position or momentum whenever you ask about it. A measurement can produce a definite result, and scientists can prepare states in which one property is known with extraordinary accuracy. What cannot be prepared is a state in which both properties possess unlimited sharpness simultaneously. The principle also does not prevent physicists from predicting motion. They can calculate how a localized wave packet changes, how its range of possible positions spreads over time, and how forces shift its momentum distribution. Quantum mechanics replaces a single classical trajectory with a carefully evolving structure of probabilities. This becomes important inside atoms, where extreme confinement near a nucleus increases the range of possible electron momenta and therefore raises the energy associated with that confinement. Similar reasoning helps explain why microscopic systems cannot simply be compressed into perfectly motionless points. At human scales, the uncertainties are so small compared with the size and momentum of everyday objects that a thrown ball still appears to follow one clear path. But beneath that familiar path lies a limit no refinement of technology can remove. Nature does not always provide an object with both a perfectly fixed place and a perfectly fixed motion waiting to be revealed. The closer you force the answer to, "Where is it?" the less narrowly the universe can answer, "How is it moving?" as though precision itself must be distributed rather than possessed all at once. Energy can fluctuate within limits set by quantum mechanics. A quantum system can be prepared with a perfectly stable average energy, while an individual measurement still refuses to return the same value every time. This is what energy fluctuation means in its most careful scientific sense. If a system occupies one exact energy state, repeated ideal energy measurements will produce that same result. So quantum mechanics does not require every object to experience a constant random trembling of its total energy. But many useful quantum states are combinations of several energy states. In that case, the energy is not sharply defined, and repeated measurements on identically prepared systems can produce different allowed values with predictable probabilities. The average remains governed by the state, while the spread of results describes its energy uncertainty. Energy can also vary when a system interacts with an external field, exchanges radiation with its surroundings, or is observed over a limited time. This is where the energy-time uncertainty relation is often distorted into the claim that nature freely borrows energy as long as it repays it quickly. That phrase may be memorable, but it is not a literal law permitting temporary violations of energy conservation. Time is not usually treated as a quantum observable in the same way as position, and the relationship more carefully connects an energy spread with the timescale over which a state changes, or a short-lived process can be resolved. An unstable excited state, for example, survives only for a limited average time, and therefore produces an emission line with a small natural width, rather than one infinitely sharp energy. The shorter the lifetime, the broader that width tends to be. In rapidly changing interactions, a brief observation may also be unable to distinguish energies with perfect resolution, much as a very short fragment of sound makes its exact frequency harder to identify. None of this creates usable energy from nothing. When a system gains or loses energy, the full interaction must still respect conservation laws, including the energy carried by measuring devices, fields, and surrounding matter. Even the fluctuations associated with quantum fields do not function as a hidden bank from which particles take illegal loans. The deeper truth is more subtle. Energy can be exact in some states, distributed across possibilities in others, and limited in precision when change occurs too quickly to define it sharply. Quantum mechanics does not abolish conservation. It reveals that the energy assigned to one fragile system may not always be a single permanent number, and that what remains constant in the complete physical story can look uncertain when you examine only one part of it. Atoms can absorb and release energy, only in specific amounts. Shine the wrong color of light on an isolated atom, and the atom may ignore it almost completely, but choose exactly the right energy, and the interaction can suddenly become possible. This selective behavior arises because the bound electrons in an atom are permitted to occupy particular energy states rather than every value along a continuous slope. To move an electron from a lower bound state to a higher one, the atom must absorb an amount of energy matching the difference between those states. A photon carrying too little energy cannot lift the electron part way and leave it suspended between levels, while a photon with a different energy may fail to drive that particular transition. When an excited atom returns to a lower state, it can release the energy difference as a photon with a characteristic frequency. This produces the spectral lines through which atoms reveal their identities. Hydrogen, sodium, neon, and every other element display distinct patterns because their nuclear charge, electron arrangement, and internal interactions create different sets of allowed energies. These lines allow scientists to identify substances in laboratory flames, distant stars, interstellar clouds, and planetary atmospheres without physically collecting the material. Yet the simple image of an electron jumping between two fixed shelves needs refinement. The transition does not require a tiny object to travel through the space between classical orbits. The entire quantum state of the atom changes, and the probability of that change depends on how the light interacts with the shapes and symmetries of the initial and final states. Some transitions are strongly allowed, others are weak, and some are forbidden by ordinary selection rules, but can still occur through slower or more complex processes. Atomic energy is also not entirely discrete under every circumstance. If enough energy is supplied to remove an electron completely, the atom becomes ionized, and the free electron can carry a continuous range of additional kinetic energies. Real spectral lines are not infinitely thin either. Motion, collisions, external fields, and the finite lifetime of excited states can broaden or split them. Even with these complications, the central rule survives. Bound atoms respond to energy in structured amounts. Matter does not absorb every frequency equally, and it does not release light as an arbitrary wash of energy. It answers with a coded pattern shaped by its internal quantum architecture. When you examine an atomic spectrum, you are seeing more than colored lines. You are seeing the permitted distances between invisible states, as though each atom carries a private ladder whose spacing can be read from the light it accepts and the light it gives back. Photons carry discrete packets of electromagnetic energy. Light may spread across a room like a smooth wave, yet whenever it gives energy to matter, it does so in indivisible events. These units are called photons, the quantum excitations of the electromagnetic field. A photon is not best imagined as a tiny glowing pellet surrounded by darkness, because its quantum state can extend across space and display interference, diffraction, and polarization. What makes it particle-like is the way electromagnetic energy is emitted, absorbed, and detected in discrete amounts. When light reaches a sensitive detector, the response appears as separate electrical pulses rather than as an infinitely divisible trickle. One photon may release an electron in the detector, which then triggers an amplified signal large enough for instruments to record. The photon is absorbed as a complete unit. Half of its energy does not remain behind as a smaller photon of the same frequency. If a source sends more photons during a given interval, the beam carries more total energy and generally appears more intense, but each photon still transfers its own packet when an interaction occurs. This distinction explains why a beam can be weakened by reducing the number of photons without changing the energy carried by each surviving photon. Photons also have no rest mass, yet they carry momentum and can push on matter. The pressure of sunlight is tiny, but it is measurable, and carefully designed light beams can move microscopic objects or cool atoms by changing their motion. A photon can travel through empty space, be redirected by a mirror, pass through transparent material, or be absorbed by an atom. But between emission and detection, quantum physics does not always provide the simple path of a miniature bullet. What remains precisely defined is the structure of the possible interaction and the amount of energy transferred when the event becomes real. The idea of photons emerged because classical waves alone could not explain why matter exchanges light in particular amounts, or why weak light produces separated detection events. Yet the photon does not replace the wave picture, it deepens it. The electromagnetic field evolves with wave-like behavior, while its energy arrives in quantized exchanges. You live inside an ocean of light that appears continuous, because an ordinary lamp sends an enormous number of photons every second. Beneath that apparent smoothness, however, every reflection entering your eyes and every signal crossing a fiber optic cable is built from individual quantum encounters. Light does not pour energy into matter as an endlessly divisible fluid. It arrives through distinct acts, each small enough to vanish into the brightness of daily life, yet precise enough to carry the colors of stars across the universe. Higher frequency light carries more energy per photon. Two beams can appear equally bright, while the photons inside them carry very different amounts of energy. The energy of a photon is determined by the frequency of the light. The faster the electromagnetic field oscillates, the more energy each photon carries. Radio waves occupy the low-frequency end of the spectrum, followed by microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays at progressively higher frequencies. This means a single ultraviolet photon carries more energy than a visible photon, while an X-ray photon carries far more than either. Brightness and photon energy must therefore be kept separate. A powerful red lamp can deliver more total energy each second than a weak ultraviolet source because it sends vastly more photons, even though every ultraviolet photon is individually more energetic. This distinction explains why different kinds of light affect matter in different ways. Low-energy photons can make molecules rotate or vibrate and can warm materials when many are absorbed. Visible photons can trigger chemical changes in pigments, including the molecules involved in vision and photosynthesis. Ultraviolet photons may carry enough energy to alter or break certain molecular bonds, which is why excessive exposure can damage cells and DNA. X-rays and gamma rays can remove tightly bound electrons from atoms, creating ions and producing biological damage through mechanisms that ordinary visible light usually cannot trigger one photon at a time. The danger does not come from an invisible substance added to high-frequency light. It comes from the larger packet of energy delivered in each individual interaction. Frequency also determines color within the visible range, though color itself is the brain's interpretation of signals created when photons stimulate light-sensitive cells in the eye. Violet photons carry more energy than red photons, but violet light does not necessarily look brighter, because human vision has different sensitivity across the spectrum, and brightness also depends on photon number. Increasing the intensity of red light sends more red photons. It does not transform them into blue photons. To change the energy of each photon, the frequency must change. This is why a sufficiently bright low-frequency beam cannot always reproduce the effect of a much weaker high-frequency beam. Some processes require a minimum amount of energy in one interaction, and delivering many smaller packets separately may not be equivalent because the system can release or redistribute the energy between arrivals. There are specialized multiphoton processes in which several photons are absorbed nearly simultaneously, but these require intense conditions and do not erase the basic rule. The electromagnetic spectrum is therefore not merely a row of different colors and invisible waves. It is a scale of energy per photon. As you move upward in frequency, each quantum of light becomes capable of opening physical doors that lower energy photons cannot easily unlock, revealing that the rhythm of a wave determines the strength of every individual encounter it can make. A dim light beam can be reduced to individual photons. Dim a light beam far enough, and the smooth stream you imagine begins to reveal itself as a sequence of separated detector clicks. Researchers can place filters and attenuators in the path of a laser until the average number of photons passing through during a chosen interval becomes much less than 1. Most intervals then contain no photon at all. Some contain 1, and a small fraction contain more than 1. A weakened laser is therefore not automatically a perfect single photon source. Its photon numbers follow a statistical distribution, and no ordinary attenuation method can guarantee that every pulse contains exactly 1 photon. To create more reliable single photons, scientists use special sources such as individual atoms, trapped ions, quantum dots, or correlated photon pair systems. In a pair source, detecting one photon can announce or herald that its partner has been produced, allowing experiments to know when a photon is available. These faint signals require detectors capable of converting one absorbed photon into a measurable electrical avalanche or another amplified response. The detector does not show a tiny point of light traveling toward it. It records a localized event at the end of the photon's journey. Repeating the experiment many times reveals the probability pattern governing where and when those events occur. One of the clearest tests of genuine single-photon behavior uses a beam splitter. Classical light can be divided so that energy reaches both outputs, but a single photon produces one complete detection event in one output or the other. It is never detected as two half-photons at the same moment. When scientists observe a strong suppression of simultaneous clicks in two detectors, a property known as anti-bunching, they gain evidence that the source is emitting photons one at a time. This ability is essential for quantum communication, precision measurements, and experiments that test the foundations of physics. It also reveals why extremely weak light does not simply become a fainter version of an ordinary wave in every respect. At high intensity, countless detection events arrive so rapidly that their discreteness is hidden and the beam appears continuous. At low intensity, the gaps become visible. Darkness occupies most moments, interrupted by individual exchanges of energy. Even then, the arrival time of the next photon is usually not predictable with certainty. The source provides probabilities, and the detector produces events. Human vision normally combines large numbers of photons into a stable scene. But under carefully controlled conditions, even biological eyes may respond to very small numbers. Though perception is influenced by neural noise and does not function as a perfect photon counter, a dim beam therefore offers a quiet demonstration of quantization. Reduce the flow of light and continuity dissolves into waiting. Nothing arrives, then one event appears, then silence returns, as though brightness itself were assembled from countless individual moments that become smooth only because your senses are too slow to separate them. A single photon can trigger a detectable event. One quantum of light can arrive so quietly that no human sense notices it, yet a carefully prepared detector can turn that single arrival into a signal large enough to measure. The process begins when one photon is absorbed by a sensitive material and transfers its energy to an electron. That first electron may be almost impossibly small as an electrical event, so the detector must amplify what happened without pretending that several photons arrived. In a photomultiplier tube, the released electron is accelerated toward a sequence of surfaces, knocking out several new electrons at each stage until the original absorption becomes a measurable pulse. In an avalanche photodiode, a strong electric field causes the first mobile charge to collide with the material and generate more charge carriers, producing a rapid cascade. Superconducting detectors use a different strategy. A photon disturbs an extremely cold electrical state, briefly changing the resistance or current in a way sensitive instruments can record. In every case, the large output does not come from the photon alone. External electrical power supplies most of the amplified energy, while the photon acts as the trigger that decides when the cascade begins. This is similar to a tiny spark opening a gate behind which far more energy is already waiting. Real detectors are not perfect. They can produce dark counts even when no photon has arrived, lose photons through reflection or inefficient absorption, and sometimes need time to recover before detecting another event. Scientists therefore compare signals with background noise, control temperature, and calculate the probability that a recorded pulse truly came from light. Even with these limitations, modern instruments can register single photons with extraordinary efficiency and timing precision. This ability allows astronomers to study extremely faint objects, doctors to image weak biological signals, engineers to test quantum communication systems, and physicists to observe processes that would vanish inside ordinary brightness. A single photon does not arrive with a visible label announcing its history, color, or path, but its absorption can leave one irreversible mark. Something with no rest mass, traveling silently through darkness, can release one electron and begin a chain containing millions more. The event reminds you that detection is often not the passive discovery of a tiny object. It is the amplification of a microscopic encounter until the larger world can no longer ignore that it happened. Human eyes can respond to extremely small numbers of photons. Your vision begins near a boundary where light becomes so scarce that seeing is partly a question of biology and partly a question of chance. In darkness, the most sensitive cells in the human retina are rods, slender photoreceptors, specialized not for color or fine detail, but for detecting extremely weak light. Inside each rod are molecules containing a light-sensitive pigment called rhodopsin. When one photon is absorbed, it can change the shape of a single retinal molecule, beginning a biochemical amplification chain that alters the electrical state of the entire cell. One microscopic event can therefore influence the signals sent toward the brain. Laboratory experiments have shown that individual rod cells can respond to single absorbed photons, an astonishing level of sensitivity for living tissue. Conscious vision, however, is more demanding. Not every photon entering the eye reaches a rod. Many are reflected, absorbed by other tissues, or miss the most sensitive region. The retina also produces spontaneous molecular events and electrical noise that can resemble weak light signals. To avoid making you see constant false flashes, neural circuits combine information across cells and apply thresholds before passing a reliable signal onward. Classic experiments found that dark-adapted people could sometimes report a faint flash when only a small number of photons reached the eye, although the exact number absorbed by the retina was lower than the number emitted by the apparatus. More recent studies have explored whether people can perform slightly better than chance when experimental pulses are prepared with extremely small photon numbers, even approaching single photon conditions. But the conscious perception of one photon remains difficult to establish cleanly because transmission losses, biological variability, expectation, and noise must all be separated. The safest conclusion is that the human visual system operates remarkably close to the physical limit of light detection. While a reliable visual experience usually depends on more than one photon and on complex processing after absorption, sensitivity also changes with adaptation. Spend 20 or 30 minutes in darkness, and chemical pigments regenerate while your nervous system gradually shifts toward rod-dominated vision. Colors fade, detail weakens, and objects become easier to notice when you look slightly beside them because rods are more abundant away from the exact center of vision. You do not experience the photon itself. You experience the brain's interpretation of a signal that began with one molecule changing shape in one cell. A star at the edge of visibility may therefore enter your awareness through only a handful of successful quantum events, each surviving a long journey through space, the optics of your eye, the uncertainty of retinal chemistry, and the filtering of your brain before becoming the faintest impression that something is there. The photoelectric effect revealed that light arrives in packets. A metal surface exposed to brighter light can remain completely silent, while a much weaker beam of the right frequency can release electrons almost immediately. This contradiction helped reveal that light exchanges energy in packets, rather than delivering it as a perfectly continuous wave. In the photoelectric effect, light shines on a material and electrons are emitted from its surface. Classical wave reasoning suggested that increasing the brightness should eventually provide enough energy to free electrons, regardless of color, perhaps after the metal had absorbed light for a while. Experiments showed something very different. Below a material-dependent threshold frequency, no electrons emerged, even when the light was intense. Above that threshold, electrons could be released without a noticeable delay, even from weak illumination. Making the light brighter increased the number of emitted electrons, but it did not automatically give each electron more kinetic energy. Raising the frequency did. In 1905, Albert Einstein explained these observations by proposing that light delivers energy in individual quanta, later called photons. One photon transfers its energy to one electron in the simplest event. Part of that energy is used to overcome the binding that holds the electron inside the material, a minimum cost called the work function. Any energy remaining can appear as the motion of the emitted electron. A low-frequency photon may carry too little energy to pay that cost, and sending many such photons ordinarily does not help because each absorption event arrives as a separate insufficient packet. A higher frequency photon can cross the threshold in one encounter. Robert Millikan later measured the effect with great precision, confirming the relationship between light frequency and electron energy, even though he had initially doubted Einstein's interpretation. The photoelectric effect did not prove that light is only a stream of classical particles. Light still produces interference and diffraction, and its full behavior requires quantum theory rather than the replacement of waves with tiny pellets. What the experiment established was that energy transfer between light and matter is quantized. This principle now operates inside solar cells, light sensors, camera chips, automatic doors, astronomical instruments, and devices that convert faint illumination into electrical signals. Sunlight striking a solar panel frees charge carriers only when the material and photon energies permit the process, turning an insight from early quantum physics into a source of modern power. The photoelectric effect changed the meaning of brightness and color at a fundamental level. Brightness often tells you how many photons arrive, while frequency tells you how much energy each one carries. Matter does not merely feel the average wash of the beam. It responds encounter by encounter, revealing that beneath continuous-looking light lies a sequence of indivisible exchanges, each photon arriving with enough energy to open a door or not enough to move it at all. Light can behave like both a wave and a stream of particles. Light refuses to choose between the two pictures. Human intuition keeps trying to impose upon it. Send it through a narrow opening and it spreads outward like a wave. Allow two portions of it to overlap and they can form bright and dark bands through interference. Pass it through certain materials and its polarization can be rotated, filtered, and combined in ways that belong naturally to waves. Yet place a sensitive detector in its path, and light does not deposit energy as a smooth film divided across the entire surface. It produces localized events, one absorption at a time, as though the energy arrived in countable units. This is often called wave-particle duality, but the phrase can suggest that light secretly changes costumes, becoming a wave during travel and a particle during detection. Quantum physics offers a more careful lesson. Wave and particle are incomplete classical models, each capturing only part of light's behavior. A photon is not an ordinary bead riding on an invisible wave, and the electromagnetic field is not merely a continuous substance that breaks into pieces at the detector. The quantum description contains a state that can spread, interfere, and carry phase information, while interactions with matter produce discrete exchanges. Which feature becomes visible depends on the experiment you construct. An arrangement designed to preserve several optical routes can reveal interference, while an arrangement that records where energy was absorbed reveals separated events. You cannot combine every classical expectation into one simple picture without contradiction, because the quantum object is more fundamental than either borrowed image. This principle is known as complementarity. Experiments can reveal different, mutually necessary aspects of the same physical system, even when no single classical story contains them all. The result is not an excuse to say, light can be anything you imagine. Its behavior is governed by precise rules that predict diffraction patterns, detection statistics, polarization effects, and energy transfers with extraordinary accuracy. The mystery lies in interpretation, not in experimental confusion. Light behaves consistently. It is your categories that fail to contain it. When a beam crosses a room, it is not required to resemble a tiny projectile or a ripple on water at every hidden moment. It evolves as a quantum field and meets matter through quantized interactions. The wave and particle descriptions are therefore not two competing truths, waiting for one to defeat the other. They are two windows cut into a structure larger than either view, reminding you that reality can be exact without being easily pictured. And that understanding sometimes begins when you stop demanding that nature resemble the objects your senses already know. Matter can display wave-like properties. Particle of matter can strike a detector at one precise location and still arrive according to a pattern created by diffraction, phase, and interference. This idea was proposed by Louis de Broglie in the 1920s, when he suggested that the wave-like character found in light might also belong to material particles. At the time, an electron was usually imagined as a tiny charged object, so assigning it a wavelength seemed almost unreasonable. The proposal became physical reality when electrons were directed toward crystals and scattered into distinct angular patterns. The regularly spaced atoms inside the crystal acted like a microscopic diffraction structure, and the outgoing electrons formed distributions that could not be explained by classical particles, bouncing independently from fixed points. Their motion had to be described using matter waves. Later experiments extended the effect to neutrons, atoms, and increasingly complex systems, revealing that wave-like behavior is not a special decoration added only to light. It is a general feature of quantum objects. This does not mean a moving electron becomes a vibrating substance spread through space, in the same way that water rises and falls in an ocean wave. The wave represents the structure of its quantum state, including how possible outcomes combine and where detections are likely to occur. Each electron still produces one complete event when absorbed, but the arrangement of many events reflects the propagation of that state. Matter waves also respond to their environment in useful ways. Neutrons can penetrate materials and diffract from atomic nuclei or magnetic structures, allowing scientists to study the interior arrangement of solids. Atoms can be split along different routes and recombined in interferometers sensitive to gravity, acceleration, and rotation. These instruments do not rely on the material object physically dissolving into a mist. They rely on preserving a coherent relationship between alternative motions long enough for their phases to be compared. The discovery of matter waves erased an ancient boundary between substance and radiation. Matter was no longer permitted to remain purely particle-like, while light carried all the wave behavior. Both became expressions of a deeper quantum framework in which propagation and detection obey different parts of the same description. The stone in your hand does not visibly diffract because its wave-like features are hidden by scale, complexity, and interaction, not because its matter belongs to a different set of fundamental laws. Beneath every apparently solid trajectory lies a quantum wavelength, usually far too small and fragile to notice, but always present in the rules that guide matter from one physical encounter to the next. The wavelength of matter becomes smaller as momentum increases. Push a quantum particle to greater momentum, and the wave associated with its motion becomes more tightly compressed. This inverse relationship is central to the idea of matter waves. Slow-moving particles possess longer wavelengths, while particles carrying greater momentum possess shorter ones. Momentum depends not only on speed but also on mass, which is why a fast electron can still have a wavelength large enough to reveal in carefully designed experiments, while a moving car has a wavelength so unimaginably tiny that no ordinary apparatus could detect its diffraction. The relationship explains why quantum wave behavior is obvious for microscopic particles, but disappears from daily experience without requiring a sudden change in physical law. Your body has momentum as you walk across a room, and in principle, a matter wavelength can be associated with that motion. Yet it is vastly smaller than an atomic nucleus and continually disrupted by interactions with air, light, heat, and the floor. No realistic doorway or laboratory grating could separate your possible paths widely enough to reveal a human-scale interference pattern. For electrons, however, the wavelength can be comparable to the spacing between atoms in a crystal, making diffraction measurable. increase the electron's momentum, and the wavelength shrinks, allowing its quantum state to respond to finer spatial details. This connection between wavelength and resolution has become enormously important in science, because smaller wavelengths can distinguish structures that longer waves blur together. Yet greater momentum does not simply provide unlimited vision. High-energy particles may damage samples, penetrate differently, produce unwanted interactions, or require more difficult control. The useful scale depends on matching the wavelength to the structure being investigated. The inverse relationship also helps explain how classical motion emerges. When momentum is large, the associated wavelength becomes so short that wave effects average out across the dimensions of ordinary objects. Many neighboring alternatives cancel, leaving a narrow range of motion that resembles a definite classical route. At lower momenta and smaller scales, the wavelength can stretch across several possible paths, making interference easier to observe. This means wave behavior is not determined by size alone. The same kind of particle may display different quantum patterns depending on how it is prepared and how much momentum it carries. A neutron moving slowly can have a wavelength useful for studying crystal lattices, while a faster neutron probes different length scales. The particle has not changed its identity. The spatial rhythm of its quantum state has changed. Momentum, therefore, does more than describe how difficult something is to stop. At the quantum level, it determines the fineness of the wave pattern through which motion is expressed. The faster or heavier the traveler becomes, the shorter that hidden rhythm grows, until the wave is still present in theory, but folded so tightly that the world appears to offer only one smooth and ordinary path. Electron microscopes use matter waves to see tiny structures. A beam of electrons can reveal structures so small that visible light passes over them without ever noticing they are there. Ordinary microscopes are limited because light cannot clearly resolve details much smaller than its wavelength, so even the finest glass lenses eventually reach a boundary beyond which the image becomes blurred. Electrons offer another path. When accelerated through an electron microscope, they carry extremely short matter wavelengths, allowing them to respond to features far smaller than those visible with ordinary light. In a transmission electron microscope, a carefully focused beam passes through an exceptionally thin specimen. Some electrons travel through relatively easily, while others are scattered by atomic nuclei, electron clouds, crystal planes, or variations in thickness. Electromagnetic lenses then guide the surviving electrons toward a detector, converting their distribution into an image. Dense regions often scatter more strongly and appear with different contrast from lighter or thinner regions, allowing scientists to examine viruses, cell structures, nanoparticles, defects in metals, and the arrangement of atoms in crystals. A scanning electron microscope works differently. Instead of sending electrons through the sample, it sweeps a narrow beam across the surface and measures signals released from each location, building an image with remarkable depth and surface detail. The pictures produced by these instruments are not direct photographs in the everyday sense. Electrons are invisible to your eyes, and the colors often added to microscope images are chosen later to separate structures or make patterns easier to understand. The sample may also need to be dried, sliced, frozen, placed in a vacuum, or coated with a conducting material, meaning the image must always be interpreted with knowledge of how it was prepared. Greater resolution also brings risks. A powerful electron beam can heat, charge, or damage delicate material, so researchers must balance clarity against destruction. Even so, electron microscopy has transformed science because it turns the wave behavior of matter into a practical instrument. The same quantum property that once seemed like an abstract challenge to common sense now allows you to inspect the machinery inside cells, locate single defects that weaken advanced materials, and distinguish rows of atoms separated by distances far beyond human vision. You do not see the electron wave itself. You see the evidence left behind when that wave meets structure, scatters differently from different regions, and carries microscopic information outward. In this way, matter becomes the light by which matter is examined, And the invisible world is not enlarged by imagination, but reconstructed from the paths of electrons, shaped by things too small for any eye to see. Quantum interference can measure distances with extraordinary precision. A movement far smaller than an atom can become measurable when it slightly shifts the phase of a quantum wave. Interferometry works by dividing a wave into two routes, allowing each part to experience a different journey and then bringing the routes back together. If both paths remain unchanged, their phases combine in a stable pattern. But if one path grows even slightly longer, or if gravity, acceleration, rotation, temperature, or another influence alters one route more than the other, the returning waves no longer line up in exactly the same way. The resulting interference pattern shifts, turning an almost invisible change in distance into a detectable change in brightness or particle counts. The power of the method comes from comparison rather than direct inspection. Scientists do not need a ruler with markings small enough to display the motion. They need a stable wave whose phase changes predictably as it travels. Optical interferometers use light because its waves can remain coherent over carefully controlled paths. Devices such as laser interferometers can measure tiny mirror movements, surface distortions, and changes in refractive index. The gravitational wave observatories known as LIGO used enormous laser interferometers to detect distortions in space-time produced by distant cosmic collisions. The mirrors in their long arms did not visibly swing. Instead, the relative path lengths changed by an extraordinarily small amount, shifting the interference of the returning light enough for sensitive instruments to identify the signal. Quantum interference can also use matter waves. In an atom interferometer, a cloud of atoms is placed into a controlled combination of different paths using pulses of light. Gravity or acceleration changes the phase accumulated along each route, and when the atomic paths are recombined, the final population of detected states reveals the difference. Such systems can measure gravitational acceleration, rotation, magnetic fields, and changes in height with exceptional sensitivity. Yet precision does not arrive automatically. Vibrations from traffic, thermal expansion, air currents, imperfect lasers, electrical noise, and even distant environmental movement can imitate or conceal the effect being measured. Instruments must be isolated, calibrated, and compared against known references, while quantum noise places limits on how accurately phase can be read. Researchers can sometimes improve sensitivity using specially prepared states of light or atoms, but these states are fragile and difficult to preserve. Interference therefore transforms measurement into an art of maintaining relationships. Neither path alone needs to reveal the answer. The information appears in the difference between them. A tiny displacement changes the history of one wave relative to another, and when those histories meet again, the shift becomes visible. The universe may hide its smallest movements from every ordinary ruler, yet a coherent quantum wave can remember the length of its journey so precisely that even a nearly impossible change leaves a pattern behind. Atomic clocks depend on stable quantum transitions. The most accurate clocks do not listen for a pendulum or watch a crystal vibrate. They tune themselves to the natural rhythm of atoms. Every atom possesses specific quantum transitions between allowed internal states, and radiation with the right frequency can drive the atom from one state to another. Because atoms of the same kind share the same fundamental properties, this transition frequency can serve as an extraordinarily consistent reference. An atomic clock begins with an oscillator, usually an electronic microwave source or a laser, whose frequency can be adjusted. A group of carefully prepared atoms is exposed to that radiation, and the clock measures how strongly the atoms respond. If the oscillator is slightly too fast or too slow, fewer atoms make the desired transition. A feedback system corrects the oscillator until its frequency remains centered on the atomic resonance. The clock then counts cycles of this stabilized signal to measure time. The internationally defined second is based on a microwave transition in cesium-133 atoms. 1 second corresponds to a fixed number of cycles associated with that transition under carefully specified conditions. Cesium does not emit a ticking sound. and an individual atom is not being used like a tiny mechanical watch. The clock observes the statistical response of many atoms and continually steers an external oscillator toward the frequency nature provides. Great care is required because atoms are not completely isolated from their surroundings. Magnetic fields can shift energy levels, collisions can disturb them, motion can change the apparent frequency through the Doppler effect, and heat can expose them to background radiation. Atomic clock laboratories cool atoms, control fields, reduce collisions, and design measurement sequences that expose and correct these effects. Newer optical clocks use transitions at much higher frequencies than cesium microwave clocks, often in trapped ions or neutral atoms held in grids of laser light. A higher frequency oscillation provides more cycles within each second, potentially allowing smaller timing differences to be resolved, though stability, accuracy, and systematic errors must all be mastered before a clock can become a standard. These instruments are so sensitive that a clock placed slightly higher in Earth's gravitational field can tick at a detectably different rate from one below it, turning relativity into an everyday laboratory effect. Accurate timing also supports navigation, telecommunications, electrical networks, astronomy, and scientific comparisons across continents. An atomic clock does not claim that time itself is made from atomic pulses. It creates a stable way to compare duration by choosing one repeatable quantum event as a reference. Human clocks once followed shadows, flowing water and swinging pendulums. Today, the second is anchored to transitions hidden inside atoms, as though civilization learned to measure time by listening not to the motion of the sky, but to one of matter's quietest and most dependable internal notes. GPS timing ultimately relies on quantum mechanical clocks. Every time your phone places a blue dot on a map, it is solving a timing problem so delicate that an error of only a few billionths of a second can shift the calculated position by several meters. GPS satellites do not simply look down and identify where you are. Each satellite continuously broadcasts a coded radio signal containing the exact time of transmission and information about its orbit. Your receiver compares the arrival times of signals from several satellites, estimates how long each signal traveled at the speed of light, and converts those travel times into distances. By finding the point consistent with several measured distances, it calculates your location and corrects the imperfect clock inside the receiver at the same time. This entire process depends on the satellites carrying highly stable atomic clocks, commonly based on cesium or rubidium standards, whose frequencies are controlled by specific quantum transitions inside atoms. A mechanical watch or ordinary electronic clock would drift too quickly for navigation on this scale. Even atomic clocks in orbit cannot simply be treated as identical to clocks on Earth, because relativity changes their rates. The satellites move rapidly, which makes their clocks run slightly slower according to special relativity. But they also orbit where Earth's gravity is weaker, which makes them run faster according to general relativity. The gravitational effect is larger, so without correction, the satellite clocks would gain roughly 38 microseconds per day relative to clocks on Earth. That may sound insignificant, yet light travels more than 11 kilometers during that interval. If engineers ignored the correction, GPS positions would accumulate enormous errors within a single day. The system therefore combines quantum physics, radio engineering, orbital mechanics, and Einstein's description of time into one invisible calculation repeated whenever you request directions. Synchronize a mobile network, guide an aircraft, track a shipment, or coordinate parts of an electrical grid. GPS does not prove that space contains a universal clock shared by everyone. It demonstrates the opposite. Clocks moving differently and resting in different gravitational conditions do not agree automatically, so their rates must be predicted and compared with extraordinary care. Beneath the simplicity of a map application lies a constellation of satellites carrying quantum references through curved space-time, announcing their time with enough precision for a receiver in your hand to discover where it is. You may feel that the location appears instantly, but the answer is built from light crossing space, atoms keeping rhythm, and a universe in which even time must be corrected before distance can be known. Quantum tunneling allows radioactive decay to occur. Inside certain unstable atomic nuclei, a cluster of particles can remain trapped for years, centuries, or billions of years before escaping through a barrier it never possesses enough classical energy to climb. This is the quantum foundation of alpha decay, a form of radioactivity found in heavy elements such as uranium and radium. An alpha particle consists of 2 protons and 2 neutrons bound tightly together, the same combination found in a helium nucleus. Within a heavy nucleus, the strong nuclear force can hold this cluster close to the remaining protons and neutrons, but once the alpha particle moves far enough outward, the electrical repulsion between its positive charge and the positive charge of the daughter nucleus pushes it away. Between the inner region, where the nuclear force binds it, and the outer region, where electrical repulsion can accelerate, it lies an energy barrier. According to classical physics, an alpha particle whose energy is below the top of that barrier should remain imprisoned forever. Quantum mechanics gives its state a small but non-zero presence beyond the forbidden region, creating a probability that the particle will emerge outside and then be driven away. The nucleus does not gradually weaken until the particle drills through, nor does the alpha particle secretly gain the missing energy for a moment. The decay releases energy because the final arrangement has less total energy than the original nucleus. Tunneling explains how the transformation can begin despite the intervening barrier. The probability is extremely sensitive to the barrier's width and height. A small difference in nuclear energy can change a half-life by many orders of magnitude, which helps explain why one isotope may decay almost immediately, while another survives longer than human civilization. This relationship was recognized in the Geiger-Nuttall law before quantum theory fully explained it. Alpha particles emitted with greater energy tend to come from nuclei with shorter half-lives because they tunnel through the barrier more easily. Still, no theory predicts the exact moment when one particular nucleus will decay. It predicts the probability for a large collection. A sample's half-life tells you how long it takes, on average, for half of its unstable nuclei to transform, not when any chosen atom must change. One nucleus may decay seconds after it forms, while an identical neighbor may remain intact for ages. Radioactive dating, nuclear medicine, detectors, and parts of Earth's internal heating all depend on this statistical process. What looks from the outside like matter simply aging is, at its core, a sequence of individual quantum escapes. The nucleus waits without a visible countdown, and then one possibility becomes an event, releasing a particle through a boundary that classical nature would have made permanent. Scanning tunneling microscopes can map individual atoms. Bring an electrically conducting needle close enough to a surface without allowing it to touch, and a tiny current begins to cross the remaining gap, carrying information about features smaller than almost any conventional probe can reach. This is the principle behind the scanning tunneling microscope, or STM, invented in the early 1980s. Its tip is sharpened until the outermost region may effectively end in a single atom, then positioned only a fraction of a nanometer above a conducting or semiconducting sample. A voltage is applied between the tip and the surface. Classical physics would treat the vacuum gap as an insulating barrier, but electrons have a small probability of tunneling across it. The resulting current is extraordinarily sensitive to distance. Move the tip slightly closer by less than the width of an atom, and the current can increase dramatically. Move it slightly away, and the current rapidly falls. The microscope scans the tip across the surface, while electronics monitor this tunneling current. In one common operating mode, a feedback system raises and lowers the tip to keep the current constant, and the required vertical motion is used to construct a map. In another mode, the height remains nearly fixed, while changes in current reveal variations across the sample. The final image is not a photograph of tiny solid balls illuminated by light. It represents a combination of surface shape and the local availability of electronic states through which tunneling can occur. A bright feature may indicate that the surface is physically higher, that its electrons are distributed differently, or both. Scientists must therefore understand the sample, voltage, and tip condition before interpreting the image. The instrument also demands extreme stability. Vibrations from footsteps, passing vehicles, temperature changes, and even sound can move the tip farther than the atomic details being measured. Many STMs operate on vibration-isolated platforms, in vacuum, and sometimes at very low temperatures to reduce motion and electronic noise. Despite these difficulties, the technique can resolve individual atoms, reveal defects in molecular structures, examine superconducting surfaces, and measure how electronic states vary across materials. It can even manipulate matter by carefully adjusting the tip's position and voltage. Researchers have moved individual atoms across a surface and arranged them into artificial patterns, demonstrating control at the scale where chemistry begins. Yet the STM cannot image every object. The sample must allow electrons to tunnel, so ordinary insulating materials require other techniques or special preparation. Its achievement is more focused and more profound. It transforms an exponentially sensitive quantum leakage into a practical sense of touch that never quite touches. The microscope learns the landscape by hovering above it, reading the faint current crossing an empty gap, and turning electrons that should have remained trapped into a map of the atomic world. Some computer chips depend on controlled quantum tunneling. Inside certain memory chips, information is stored by persuading electrons to cross an insulating layer that was specifically designed to stop them. This sounds like a flaw because insulation is supposed to keep charge confined, yet engineers learn to turn quantum tunneling into a controlled doorway. Flash memory, used in solid-state drives, memory cards, cameras, and phones, contains transistor-like cells with a region capable of trapping electrical charge for years. In many designs, electrons are placed onto a floating gate or charge-trapping layer surrounded by material through which ordinary conduction is extremely difficult. A sufficiently strong electric field changes the tunneling probability, allowing electrons to pass through the thin insulating barrier and become stored. Once the programming voltage is removed, the barrier again becomes extremely resistant, so the trapped charge remains in place without continuous power. That stored charge changes the voltage required to switch the cell, allowing electronic circuits to interpret the cell as a 0, a 1, or, in modern multi-level memory, one of several carefully separated values. Erasing the memory reverses the process by driving electrons back across the barrier. This is not the same as a wire carrying a normal current through a conductor. The insulating layer remains a barrier, and electrons cross only because quantum mechanics gives their wave-like states a small presence on the far side. Engineers control this probability through barrier thickness, voltage, material choice, and pulse duration. The control must be remarkably precise. If too few electrons move, the cell may not change state reliably. If too many cross, the insulating layer can be damaged. Repeated programming and erasing gradually wears the material because high electric fields create defects, trap unwanted charge, and open accidental leakage paths. This is one reason flash memory cells have limited write endurance, even though they can be read many more times. As chips shrink, the same quantum process becomes both a tool and a threat. Thin barriers make deliberate tunneling easier, but they also allow electrons to leak when they should remain trapped, shortening data retention and increasing power loss. Chip designers therefore build error correction, wear leveling, and sophisticated voltage control around a process that is fundamentally probabilistic. Your photographs and documents can remain stored without a battery because electrons have been placed behind barriers they are unlikely to cross on their own. Digital memory appears exact and permanent on the screen, yet deep inside the device, it depends on managing an improbable escape with such discipline that chance becomes engineering. Quantum mechanics explains why some materials conduct electricity. Copper wire carries current, not because its electrons race through empty tunnels like water through a pipe, but because the entire crystal provides quantum states in which electrical motion can be organized. When many atoms form a solid, Their outer electron states overlap and spread through the repeating lattice. The electrons can no longer be understood only as belonging to isolated atoms. They occupy collective states extending across the material, and an applied electric field can shift the distribution of occupied states so that a net current appears. In a good conductor, electrons near the highest occupied energies have accessible states nearby into which they can move. This availability is crucial. A material may contain an enormous number of electrons and still fail to conduct if every relevant state is filled and the next permitted states are too difficult to reach. Current requires not merely charged particles, but charged particles with allowed destinations. The crystal's periodic structure also means electrons do not behave exactly like tiny balls repeatedly crashing into every atom. Their quantum waves can travel through a perfectly ordered lattice in stable patterns. Electrical resistance appears mainly when that order is disturbed. Vibrating atoms, impurities, defects, boundaries, and other electrons scatter the moving quantum states, redirecting momentum and converting organized electrical energy into heat. As a metal warms, its atoms vibrate more strongly, usually increasing this scattering and raising resistance. Cooling reduces much of that vibration, though impurities and defects can leave a residual resistance even near absolute zero. Different materials conduct differently because their electron density, available states, crystal structure, and scattering rates are different. Copper is an excellent conductor because its electronic structure allows mobile states, and because high-purity copper can offer relatively weak resistance to their motion. Some metals conduct less effectively because their electrons scatter more strongly, or because their useful states move through the lattice less easily. In certain materials, temperature, pressure, or magnetic order can rearrange the electronic structure so dramatically that the material changes from conducting to insulating or back again. These transitions show that conductivity is not simply a permanent property carried by each atom before the solid is formed. It emerges from the collective quantum organization of the complete material. Even the idea of an electron moving through a metal must be handled carefully. Its average drift along the wire is often surprisingly slow, while the electrical influence that organizes the current travels through the circuit much faster. The lamp turns on quickly, not because one electron sprints from the switch to the bulb, but because electrons already present throughout the circuit respond collectively to the electric field. Conductivity is therefore less like individual travelers crossing a road and more like an entire crowd finding permitted ways to shift together. Matter carries electricity when its quantum architecture provides both mobile charge and room for that charge to change its state. Semiconductors work because electrons occupy quantum energy bands. The device controlling the flow of electricity inside a computer begins with a material that is neither a natural conductor nor a perfect electrical barrier. In a semiconductor such as silicon, the enormous number of atomic electron states combine into broad energy bands. At low temperatures, the lower valence band is mostly filled, while the higher conduction band is mostly empty, and a forbidden energy gap separates them. Electrons in the filled lower band cannot easily create a current because nearly all nearby states are already occupied. To become mobile, an electron must receive enough energy to cross the gap into the conduction band, leaving behind an empty state called a hole. The electron and the hole can then move through the crystal under an electric field, carrying charge in complementary ways. The size of the energy gap gives semiconductors their controllability. It is large enough to restrict current under some conditions, but small enough that heat, light, voltage, or carefully added impurities can create mobile charge carriers. Engineers modify pure silicon through doping, replacing a tiny fraction of its atoms with atoms that contribute either an extra electron or one fewer electron to the bonding structure. Material with an abundance of mobile electrons is called N-type, while material in which holes dominate is called P-type. The names do not mean the whole crystal becomes strongly negative or positive. The material remains nearly electrically neutral. They describe which kind of mobile carrier most easily responds to an applied field. When p-type and n-type regions meet, electrons and holes initially move across the boundary and recombine, leaving behind a charged region that creates an internal electric field. This p-n junction can permit current more easily in one direction than the other, forming the foundation of diodes. More elaborate structures allow a voltage applied at one region to reshape the energy landscape elsewhere, controlling whether a conducting channel exists. That principle makes transistors possible. A transistor does not need a mechanical switch to move. It changes the allowed motion of charge by altering electric fields and band alignments inside the crystal. Light can also promote electrons across the band gap, which is why related semiconductor structures can act as photodetectors or solar cells. In light-emitting devices, electrons and holes recombine and release energy as photons, with the semiconductor's band structure helping determine the emitted color. Real semiconductors are more complicated than a simple drawing of two bands. Crystal momentum, impurities, temperature, interfaces, strain, and defects all affect how easily charge moves and how efficiently light is absorbed or released. Still, the central idea remains beautifully clear. Silicon becomes useful because its electrons are restricted, but not completely trapped. The gap creates a region of control between effortless conduction and total isolation. Modern technology was built inside that narrow quantum middle, where a small voltage can decide whether billions of electrons remain unavailable or become free to carry information. Insulators and conductors differ because of their allowed electron states. Two pieces of solid matter can contain similar numbers of electrons. Yet one carries current easily, while the other refuses almost completely, because conductivity depends less on how many electrons exist than on whether those electrons have somewhere available to go. Inside a solid, the closely packed atoms create collective ranges of allowed electron energies known as bands. In a conductor such as copper, the highest occupied band is only partly filled, or it overlaps another permitted band, leaving many nearby states open. When an electric field is applied, electrons can shift into those available states and produce an organized flow of charge. An insulator presents a very different landscape. Its highest occupied states are filled, while the next available band lies across a relatively large energy gap. A weak electric field cannot easily lift electrons across that gap, so the charges remain bound within the material even though the atoms contain many electrons. This is why glass can contain enormous numbers of charged particles and still prevent an ordinary current from passing through it. The difference is not simply that electrons are loose in one material and physically glued down in another. Quantum rules determine which energy states exist, which are occupied, and whether a nearby state is available for an electron to enter. Temperature can sometimes provide enough energy for a small number of electrons to cross a gap, which is why many insulating materials become slightly more conductive when heated. But if the field grows too strong, even a good insulator can break down. Electrons may be accelerated or promoted into conducting states, producing a sudden current that can damage the material, create a spark, or form a permanent conducting path. Impurities, defects, pressure, and changes in crystal structure can also alter the allowed states so dramatically that the same substance moves closer to conducting or insulating behavior. Some advanced materials cannot even be understood through the simple picture of filled and empty bands alone, because strong interactions between electrons can block motion that an ordinary band model would predict. This reveals an important truth. Electrical behavior is not determined by individual atoms in isolation. It emerges when countless atoms form one shared quantum structure. A wire conducts and a ceramic resists because the electrons in each are offered different landscapes of permission. One material provides nearby destinations, the other places the next destination beyond a forbidden gap. What feels like a simple contrast between something that lets electricity through and something that does not is really a difference in which changes nature allows its electrons to make. Superconductors can carry current without ordinary electrical resistance. Cool certain materials below a critical temperature, and an electrical current can continue flowing without the steady loss of energy that normally warms every wire. This state is called superconductivity, and it is not merely very good conductivity. In an ordinary metal, moving electrons are scattered by vibrating atoms, impurities, crystal defects, and other disturbances, converting some of the organized electrical energy into heat. A superconductor enters a collective quantum state, in which the current cannot be slowed by these ordinary forms of scattering in the usual way. Once a current is established in a closed superconducting loop, it can persist for extremely long periods without an applied voltage continually pushing it forward. Experiments have observed persistent currents lasting for years, and the theory predicts that an ideal isolated loop could maintain them far longer. Yet zero resistance does not mean unlimited electrical power or a source of free energy. Energy must still be supplied to create the current, cool the material, generate magnetic fields, and operate the surrounding equipment. A superconductor also has limits. If it becomes too warm, carries too much current, or is exposed to a magnetic field beyond its critical strength, the superconducting state breaks down and ordinary resistance returns. Different superconductors respond to magnetic fields in different ways. In many practical materials, magnetic flux can enter through narrow quantized vortices rather than being completely excluded. If those vortices move, they can dissipate energy, so engineers pin them in place using defects deliberately introduced into the material. This allows superconducting wires and magnets to carry enormous currents while remaining stable. Superconductivity makes possible the powerful magnets used in medical imaging machines, particle accelerators, some experimental fusion devices, and specialized scientific instruments. It also supports extraordinarily sensitive magnetic sensors and circuits used in certain quantum computers. Most conventional superconductors require extremely low temperatures, often maintained with liquid helium, although high-temperature superconductors can operate at temperatures reachable with liquid nitrogen. Despite the name, these temperatures are still far colder than ordinary human environments. Researchers continue searching for materials that remain superconducting under more practical conditions, but claims of room temperature superconductivity must be treated cautiously and independently verified, especially when extreme pressure is involved. The wonder of superconductivity is not that electrons suddenly move faster. Their net drift can remain modest. What changes is the state of the material itself. Current becomes a protected collective motion that ordinary disruptions cannot easily degrade. Resistance, something that seems unavoidable whenever electricity flows through matter, turns out not to be a universal tax imposed on every current. Under the right quantum conditions, matter can carry motion without continuously forgetting it. Electrons in a superconductor can form coordinated Cooper pairs. The transformation into superconductivity begins when electrons, which normally repel one another, find a way to move as coordinated pairs. In many conventional superconductors, an electron traveling through the crystal slightly attracts the positively charged atomic lattice toward its path, creating a subtle distortion. That distortion can influence a second electron, producing an effective attraction between the two, even though their direct electrical force remains repulsive. At sufficiently low temperatures, this lattice-mediated attraction can bind electrons into what are called Cooper pairs. The electrons in a typical pair usually have opposite momenta and opposite spin orientations, so their combined motion has a balanced structure. They are not tiny partners orbiting closely around each other like a miniature binary star. A Cooper pair can be spread across a distance much larger than the spacing between atoms, overlapping with countless other pairs throughout the material. Because the pairs overlap so extensively, they cannot be treated as isolated couples moving independently. They join a single coherent quantum state with a shared phase, and it is this collective order that gives the superconducting current its unusual stability. To scatter one electron in the ordinary way, the environment may need to disrupt the coordinated state and supply enough energy to break a pair or create an excitation. At low temperatures, many everyday disturbances do not provide enough energy to do that, so the current remains protected from the usual resistance-producing collisions. This protection is described by an energy gap separating the superconducting state from certain excited states. As temperature rises, thermal motion creates more excitations and eventually destroys the pairing and shared coherence, returning the material to normal conduction. The Cooper pair explanation, developed within BCS theory, describes many superconducting metals with remarkable success, but it does not settle every case. In high-temperature superconductors and other unconventional materials, electrons also appear to pair, yet the mechanism binding them may involve magnetic interactions or other collective effects rather than the simple vibration of the crystal lattice. Understanding that mechanism remains one of condensed matter physics' major challenges. Pairing also reveals a surprising transformation in quantum statistics. Individual electrons are fermions and resist occupying an identical state. But a pair made from two electrons can behave collectively in a boson-like way, allowing enormous numbers of pairs to participate in one coordinated condition. The electrons do not lose their identity as fermions. Their relationship creates a new level of behavior that belongs to the whole material. Superconductivity therefore emerges not because one electron discovers a frictionless private road, but because vast numbers of electrons stop acting as unrelated travelers. They organize their motion so deeply that disturbing one current means disturbing an extended quantum order, showing how particles that repel at close range can still build cooperation when the surrounding material quietly carries the message between them. Magnetic fields can be expelled from a superconductor. Cool the right material through its critical temperature while a magnetic field passes through it, and the field can be pushed out as though the interior of the material has suddenly become hostile to magnetism. This is the Meissner effect, one of the defining properties of superconductivity, and it reveals that a superconductor is not merely a perfect wire with zero electrical resistance. If an ordinary conductor somehow reached zero resistance while a magnetic field was already trapped inside it, the field could remain frozen there because no resistance would exist to change the circulating currents that support it. A true superconductor behaves differently. When it enters the superconducting phase, currents appear near its surface and generate a magnetic field that opposes the applied field inside the material. The cancellation is not always perfectly complete at the atomic surface. The field can penetrate a short distance known as the penetration depth before fading rapidly, so the expulsion is a bulk property rather than an infinitely sharp wall. The behavior also depends on the type of superconductor. Type I superconductors can exclude magnetic fields almost completely until a critical field is reached, after which superconductivity breaks down abruptly. Type II superconductors, which include many materials used in strong magnets, allow magnetic flux to enter through narrow tubes called vortices. Once the field passes a lower critical value, each vortex carries a precise quantum of magnetic flux and has a tiny core where the material is not fully superconducting. Between those cores, the superconducting state survives. At still stronger fields, too many vortices enter, and superconductivity eventually disappears. This mixed state allows Type II materials to function in magnetic fields far beyond those tolerated by simpler superconductors. The Meissner effect is therefore not a vague magnetic repulsion, but the macroscopic result of a coherent quantum state responding collectively to an applied field. Countless charge carriers behave as one organized system, producing surface currents without being instructed particle by particle. The magnetic field is not destroyed. It is redirected around the material or confined into quantized structures. What looks from the outside like an invisible force refusing entry is really the material reorganizing its internal motion so that the field cannot occupy it in the ordinary way. You are watching a solid object defend a quantum condition across its entire volume, turning an effect hidden in microscopic equations into a visible rearrangement of the space around it. Quantum effects allow superconductors to levitate magnets. A magnet suspended above a cold superconductor seems to have escaped gravity. Yet the most impressive part is not that it floats, but that it can remain locked in place even when the apparatus is tilted or turned upside down. Simple magnetic levitation can begin with the Meissner effect. As the superconductor excludes an applied magnetic field, currents arise that create an opposing field, producing repulsion between the superconductor and the nearby magnet. But stable demonstrations often use Type II superconductors, where the explanation becomes richer. Magnetic flux can enter these materials through quantized vortices, thin channels around which superconducting currents circulate. Real superconductors contain defects, grain boundaries, and imperfections that can pin those vortices in particular locations. Once the material is cooled in the presence of a magnet, the pattern of trapped flux becomes anchored to the internal structure. If the magnet tries to move sideways, rise, fall, or rotate, the vortices would need to shift through the material. Pinning resists that motion, producing forces that pull the system back toward its established position. This phenomenon is called flux pinning or quantum locking. It does not mean the magnet is frozen in space by a mysterious energy field, and it is not anti-gravity. Gravity still pulls downward, while magnetic forces provide an equal upward support, and, in lock demonstrations, restoring forces in other directions. Energy is also required to cool the material below its critical temperature, usually with liquid nitrogen for common high-temperature ceramic superconductors. As the superconductor warms, thermal motion weakens the superconducting state. The pinned flux becomes less stable, and the levitation eventually disappears. The dramatic floating magnet is therefore temporary, unless active refrigeration maintains the required temperature. The same principles matter beyond demonstrations. Flux pinning helps high-field superconducting magnets remain stable by preventing vortices from moving, because moving vortices can generate energy loss and heat. Engineers deliberately introduce microscopic defects to improve pinning, turning imperfection into a useful design feature. Magnetic bearings, experimental transport systems, flywheel energy storage, and precision devices can exploit the low friction and stability that superconducting levitation provides, though practical cost, cooling, and material brittleness remain serious limitations. The magnet floats not because nature has suspended its rules, but because several rules meet an exact balance. Gravity pulls, magnetic fields bend, superconducting currents respond, and quantized vortices cling to defects. The result feels impossible only because the machinery is invisible. Beneath the quiet gap between magnet and material, an entire quantum state is holding its position. Quantum computers store information in qubits. A quantum computer begins by replacing the simple certainty of an ordinary bit with a physical system whose possible answers can be controlled before one of them is finally read. A classical bit is designed to occupy one stable state labeled 0 or another labeled 1. A qubit also has two reference states, but before measurement, its quantum state can contain a carefully weighted combination of both, including a relative phase that has no ordinary classical equivalent. This does not mean the qubit stores two complete classical answers that can both be opened and read later. When measured, it produces only one result, 0 or 1, with probabilities determined by how the state was prepared. The computational value lies in manipulating the amplitudes and phases before measurement so that unwanted outcomes interfere destructively while useful outcomes become more likely. Physical qubits can be built in several ways. Superconducting circuits use tiny electrical oscillations interrupted by Josephson junctions. Trapped-ion computers store qubits in internal atomic states controlled by lasers. Photonic systems use properties of individual photons, while other approaches explore electron spins, neutral atoms, and defects inside crystals. Each platform must provide the same basic abilities: initialize the qubits, perform precise operations called quantum gates, create controlled relationships between qubits, preserve coherence long enough to complete the calculation, and measure the final results. A single qubit gate rotates the state through its available quantum possibilities, while a 2-qubit gate can create entanglement, allowing the complete information to reside in correlations that cannot be assigned independently to either qubit. Yet adding qubits does not automatically create useful computational power. Real devices suffer from noise, imperfect control, unwanted interactions, and measurement errors, because an unknown quantum state cannot simply be copied as a backup. Quantum error correction spreads logical information across many physical qubits and detects certain errors without directly reading the protected computation. This requires large numbers of high-quality qubits for every reliable logical qubit, which is one reason building a fault-tolerant quantum computer remains so difficult. Quantum machines are also not faster for every task. They are expected to offer major advantages only for particular problems, whose structure can be translated into useful interference, such as certain simulations of quantum systems, selected mathematical algorithms, and specialized searches or optimizations under carefully defined conditions. The qubit is therefore not a magical bit with infinite information inside it. It is a fragile physical object whose possibilities must be shaped with extraordinary precision. A quantum computer succeeds only when those possibilities are guided into one final measurement that carries more useful structure than chance alone could provide. A qubit can preserve a combination of 0 and 1. A qubit can hold a condition that has no honest equivalent inside an ordinary computer. It can remain poised between 0 and 1 without secretly being one of them all along. This state is called a superposition, but it should not be imagined as two readable numbers stored side by side. If you measure the qubit, you receive only one classical answer, 0 or 1, and the state that existed before measurement cannot be fully reconstructed from that single result. What the qubit preserves is a controlled combination of two reference states, including both their relative weights and a less visible feature called phase. The weights influence how frequently each result appears when the same preparation is repeated, while phase determines how the alternatives will combine during later operations. This hidden phase is one reason a qubit contains more structure than a classical coin spinning in the air. An unknown coin already has an ordinary physical orientation at every moment, even when you cannot see it. A qubit can be prepared in states for which no single predetermined 0 or 1 description reproduces every possible measurement. Scientists often represent these states as points on a sphere, with 0 and 1 at opposite ends, and countless other possible preparations distributed across the surface. This sphere is not a physical container inside the qubit. It is a map showing how the state will respond when measured in different ways. A pulse of microwave radiation, a laser, or another precisely controlled interaction can rotate the state across this map, changing both its probabilities and phase without reading it. The preservation is delicate. Stray fields, thermal noise, imperfect control, and unwanted contact with surrounding matter can disturb the phase or push the qubit toward an ordinary mixture in which the quantum relationship has been lost. Engineers therefore speak of coherence time, the limited interval during which the qubit retains enough of its carefully prepared structure to remain useful. A qubit also does not contain an infinite collection of classical bits that can all be extracted. Although describing its state requires continuous quantities, measurement cannot reveal those quantities from one copy, and only a limited classical outcome emerges from each readout. Its power lies not in storing endless readable information, but in allowing controlled operations to reshape possibilities before a final answer is demanded. You may think of 0 and 1 as two shores, while the qubit preserves not two separate travelers, but one navigable state stretched across the space between them. The computation happens while that state is still allowed to move, rotate, and retain relationships that collapse into a simpler answer only at the moment of measurement. Quantum computers gain power from interference, not simple parallel universes. The popular claim that a quantum computer solves a problem by sending copies of itself into countless parallel universes sounds dramatic, but it hides the mechanism engineers must actually control. Quantum algorithms gain their advantage from the evolution and interference of probability amplitudes. A collection of qubits can be prepared so that many computational alternatives are represented within one quantum state. Yet merely creating those alternatives does not solve anything. If the machine were measured immediately, it would return only one result, usually with little reason for that result to be useful. The difficult work is designing a sequence of gates that changes the phases of the alternatives so that paths leading toward wrong answers cancel, while paths associated with desired features reinforce one another. This is closer to shaping a complex wave than to running a normal computer independently in many worlds. The machine cannot print every intermediate possibility, inspect them all, and hand you a complete list. Most of that information remains inaccessible. A successful algorithm arranges the state so that a small amount of useful global information becomes likely to appear in the final measurement. In Grover's search algorithm, for example, repeated operations increase the amplitude connected with a marked answer while reducing the amplitudes of alternatives, offering a speed up over an unstructured classical search without testing every entry in a separately readable universe. In Shor's factoring algorithm, the crucial advantage comes from creating a periodic quantum structure and using interference to reveal information about that period, not from collecting answers from parallel copies of the machine. Quantum simulation follows another natural route. Because molecules and materials are themselves quantum systems, qubits may represent their interacting states more directly than classical bits can. Even then, useful results require carefully chosen measurements and repeated runs. The many worlds interpretation can describe a quantum computation using branching language, and some physicists find that picture meaningful, but the hardware and mathematical predictions do not depend on accepting it. Other interpretations describe the same gates, amplitudes, and outcomes without saying that literal universes perform separate calculations. This distinction matters because the parallel universe story can make quantum computing sound automatically and infinitely powerful. It is neither. Algorithms must possess a structure that interference can exploit, noise can destroy the advantage, and many ordinary tasks gain no useful speed up at all. A quantum computer is powerful, not because every possibility becomes a servant returning an answer, but because possibilities can be made to combine before any answer is read. Its strength lies in subtraction as much as addition. The wrong computational paths can be arranged to erase one another, leaving a pattern in which the information you need stands out from the silence they create. Entanglement allows qubits to share information in unusual ways. When qubits become entangled, the most complete information about them can exist in the relationship between them, rather than inside either qubit alone. Consider two qubits prepared so that measuring them always produces matching results. Each qubit by itself may look completely random, giving 0 or 1 with equal frequency, yet the pair possesses a definite joint structure. Whatever one result is, the other follows the agreed correlation. This is not the same as placing matching classical instructions inside two boxes. Entangled qubits can produce families of correlations that cannot be explained by assigning each one a full private list of predetermined answers for every possible measurement. The state belongs to the pair, and attempts to describe each qubit independently throw away information that is physically relevant to the whole. This unusual distribution of information is essential to quantum computation. Certain gates create entanglement, so that later operations act on joint patterns across many qubits, rather than on isolated values. An algorithm can encode whether several qubits have matching parity, whether a hidden pattern exists across a register, or whether an error has affected one part of a protected state. Even when no individual qubit contains the entire answer, quantum error correcting codes use this principle carefully. They spread one logical qubit across correlations among many physical qubits, allowing engineers to check error-related relationships without directly measuring and destroying the protected logical information. Entanglement also makes quantum teleportation possible. In that protocol, a shared entangled pair and an ordinary classical message allow the unknown state of one qubit to be reconstructed at another location. No physical particle is transported, no faster-than-light message is sent, and the original state does not remain behind as a duplicate. What moves is the state's usable quantum description through a process that consumes the original entanglement. In quantum networks, this could eventually connect distant processors or sensors, although losses, imperfect gates, and fragile memories remain formidable challenges. Entanglement should therefore not be described as qubits whispering secret data instantaneously to one another. Neither side can control its local random outcome well enough to transmit a message by itself. The advantage appears when the full set of relationships is later used inside a computation, communication protocol, or comparison of results. Classical information is often imagined as something stored in separate containers. Entangled information is more like a pattern woven between the containers, disappearing if you insist on cutting the fabric into independent pieces. The qubits remain physically distinct, yet the fact that matters may belong nowhere separately. It lives in the connection, showing that in quantum technology, information is not always located where the objects carrying it appear to be. Quantum errors increase when qubits interact with their environment. A qubit can lose a carefully prepared calculation without visibly breaking, simply because the surrounding world learns a little too much about it. Quantum information depends on delicate relationships between possible states, and those relationships can be disturbed by heat, stray electromagnetic fields, vibrations, imperfect control pulses, defects in materials, and countless other interactions that ordinary electronics can usually ignore. A superconducting qubit, for example, may be affected by microscopic fluctuations in electrical charge or magnetic flux, while an ion trapped in a vacuum can still be disturbed by unstable lasers, collisions with leftover gas, or unwanted motion. These influences create several kinds of error. Energy relaxation occurs when an excited qubit releases energy and falls toward a lower state, changing the value the computation was meant to preserve. Dephasing is subtler. The qubit may retain the same probabilities of producing 0 or 1, yet the relative phase connecting those possibilities gradually loses its precision. Because quantum algorithms rely on phase to create useful interference, this loss can ruin a calculation even when a simple measurement appears unchanged. Operations themselves can also be imperfect. A control pulse intended to rotate a qubit by a precise amount may rotate it slightly too far, while a gate linking two qubits may accidentally influence nearby qubits as well. These small mistakes accumulate as a circuit grows, which is why a machine containing many physical qubits is not automatically more powerful than a smaller, better controlled device. Engineers fight this problem by cooling hardware, shielding it, improving materials, calibrating gates and shortening computations. But isolation alone can never be complete, because qubits must still be controlled and measured. The same channels that make a qubit useful also create pathways through which noise can enter. Quantum error correction addresses this by encoding one logical qubit across many physical qubits, then measuring carefully chosen relationships that reveal whether an error occurred without directly exposing the protected information. If the physical error rate remains below a certain threshold, repeated correction can, in principle, keep the logical state alive much longer than any individual qubit would survive. The cost is immense. One reliable logical qubit may require many physical qubits, fast measurements, accurate feedback, and additional hardware devoted entirely to finding mistakes. The struggle to build a quantum computer is therefore not mainly a struggle to create strange states. Laboratories can already do that. The harder challenge is preventing those states from becoming ordinary before the calculation is finished. A qubit must remain connected enough to be useful and isolated enough to remember, balanced for a brief interval between control and destruction, while the environment waits at every edge to turn its fragile possibilities into irreversible noise. Quantum cryptography can reveal whether a message was intercepted. A secret quantum key can carry its own warning that someone tried to steal it, because an eavesdropper cannot inspect unknown quantum signals without risking a detectable change. This is the central promise of quantum key distribution. a method designed not to transmit the private message itself, but to let two users create a shared random key whose security can be tested using the laws of physics. In a common protocol, one person sends photons prepared in several possible polarization states, chosen from two different measurement bases. The receiver independently chooses how to measure each photon. Afterward, both users communicate openly about which bases they used, without revealing the actual measurement results, and keep only the events in which their choices were compatible. Those retained results can form the raw material for a secret key. An interceptor faces a problem. Because the sender's preparation basis is unknown, the eavesdropper must guess how to measure each photon. A wrong choice changes the state that is forwarded, introducing errors into the receiver's results. The legitimate users reveal and compare a small sample of their data. If the error rate is too high, they know the transmission may have been intercepted or corrupted and discard the key before using it. If the error remains below an acceptable limit, they apply classical procedures called error correction and privacy amplification, removing disagreements and shortening the key until any information potentially gained by an eavesdropper becomes negligibly small. This does not make every quantum communication system automatically secure. Real devices contain imperfections that ideal theories do not include. Detectors may respond differently to carefully timed signals, photon sources may occasionally emit more than one photon, and hardware can leak information through side channels. Several practical attacks have exploited such weaknesses without violating quantum mechanics at all. Modern systems therefore require strong engineering, device testing, authentication, and protocols designed to close known loopholes. Quantum key distribution also does not identify the interceptor or prevent someone from blocking the channel. It reveals suspicious disturbance and allows the users to refuse an unsafe key. Nor does it eliminate the need for classical cryptography, because the public communication used during the protocol must be authenticated so that an attacker cannot impersonate both parties. Its deepest advantage is narrower and more remarkable. Security does not depend solely on assuming that a mathematical puzzle will remain difficult for future computers. It can be grounded in the fact that unknown quantum states cannot be measured, copied, and replaced perfectly without consequence. The message may still travel through ordinary encrypted channels, but the key protecting it is born from signals that remember interference. In this form of communication, privacy is not guaranteed by hiding the existence of an observer. It is protected by arranging the exchange so that observation cannot remain completely hidden. Quantum teleportation transfers a state rather than physical matter. Nothing disappears from one laboratory and reappears intact in another when quantum teleportation succeeds. What travels is the ability to reconstruct a quantum state. The protocol begins with two distant participants who share an entangled pair of particles. One member of the pair remains with the sender, while the other is delivered to the receiver. The sender then receives a third particle carrying an unknown quantum state that must be transferred. Instead of measuring that state directly, which would reveal only limited information and disturb it, the sender performs a special joint measurement on the unknown particle and the nearby half of the entangled pair. This measurement produces one of several ordinary outcomes and destroys the original state in its initial location. The sender communicates the outcome to the receiver through a classical channel, using signals that cannot travel faster than light. Depending on the message, the receiver performs a corresponding operation on the distant particle. After that correction, the receiver's particle occupies the same quantum state that the original particle carried before the protocol began. The matter itself has not crossed the distance. The receiving particle was already waiting there, and the sending particle has not been copied. Its original state no longer exists after the joint measurement, which is why teleportation respects the rule against making perfect duplicates of unknown quantum information. Entanglement supplies the non-classical relationship required for the transfer, while the classical message determines how the receiver must complete it. Without the message, the receiver sees only a random local state and cannot extract the teleported information. This prevents faster-than-light communication and preserves ordinary causality. Quantum teleportation has been demonstrated with photons, trapped ions, atoms, superconducting circuits, and links extending through optical fibers and free space. In future quantum networks, it may allow information to move between processors without sending fragile qubits directly through every stage of a device. It can also support quantum repeaters, which aim to distribute entanglement across distances longer than a photon could survive in one uninterrupted channel. Yet practical teleportation remains demanding. The shared entanglement must be created and preserved. The joint measurement must be performed accurately. Losses must be controlled, and the receiving system must remain coherent while waiting for the classical result. Teleportation, therefore, does not offer transport for people, objects, or memories in the science fiction sense. Reconstructing a human body would require information and control beyond anything remotely possible, while the original would have to be destroyed in the process. The real achievement is quieter. A state can leave no physical trail carrying its full quantum description from one location to another, yet still be recreated faithfully through shared entanglement and a small classical message. Quantum teleportation shows that information can move without the object that first embodied it making the journey, but only because the universe prepared a relationship between the endpoints before the transfer began. Different interpretations agree on predictions, but disagree about reality. Quantum theory can tell several physicists exactly what a detector will record, while leaving them in complete disagreement about what existed before the detector clicked. This is the unusual situation created by interpretations of quantum mechanics. They generally use the same experimental data and reproduce the same established predictions, yet they tell radically different stories about the reality beneath those predictions. The traditional Copenhagen family of views treats the quantum state mainly as a tool for organizing possible measurement outcomes and resists demanding a familiar picture of what a system is doing when no result has been recorded. Bohmian mechanics restores definite particle positions and trajectories, but guides them through a non-local quantum structure that connects distant parts of a system in ways classical physics never allowed. Objective collapse theories propose that superpositions are real but do not survive indefinitely. Some new physical process too weak to notice for small systems, but increasingly powerful for larger ones, eventually selects one outcome. Relational approaches argue that properties are not absolute possessions of isolated objects, but become definite only relative to other physical systems with which they interact. Cubism goes further by treating the quantum state as an expression of an agent's expectations about future experiences, rather than as a literal object spread through space. Many Worlds removes collapse entirely and says the full quantum state continues evolving while observers become correlated with different outcomes. These interpretations are not merely different metaphors placed over one obvious reality. They disagree about whether particles have definite hidden positions, whether collapse is physical, whether the quantum state is real, whether properties exist independently, and even whether one unique outcome is fundamental. Yet when they remain empirically equivalent, an experiment performed today may not be able to choose among them. That does not make the disagreement meaningless. Interpretations guide which questions physicists consider natural, which new theories they attempt to construct, and where they search for possible deviations from standard quantum mechanics. Collapse models, for example, can be tested if they predict tiny departures from ordinary quantum behavior, while hidden variable theories must respect the experimentally confirmed limits revealed by Bell-type tests. Some interpretations may eventually inspire distinct predictions. Others may remain alternative ways of understanding the same formal structure. The unsettling lesson is that prediction and explanation are not identical achievements. A theory may calculate every observed frequency correctly, while still leaving room for incompatible accounts of what the universe is made of. Quantum mechanics forces science to confront a question it usually keeps hidden. When several descriptions produce the same measurable world, should reality be identified only with what can be tested? Or does understanding require a deeper story, even when nature has not yet shown us how to choose one? The many worlds interpretation treats every quantum outcome as continuing. In the many worlds interpretation, the universe never chooses one quantum outcome and destroys the rest. Every allowed result remains inside a continuously evolving reality. Proposed by Hugh Everett in the 1950s, this view begins by taking the ordinary quantum evolution of the wave function seriously and applying it not only to isolated particles, but also to measuring devices, laboratories, observers, and the universe as a whole. Suppose a qubit is measured and can produce either 0 or 1. Textbook language often says the state collapses randomly into one result. Many worlds removes that collapse. Instead, the qubit, the detector, and the observer become entangled in a larger state containing one branch in which 0 was recorded and another in which 1 was recorded. Each future observer remembers seeing a single definite result because the versions of the observer in different branches no longer have access to one another's records. Decoherence helps explain why these branches become effectively independent. Their information spreads into the environment through photons, heat, air, and countless microscopic interactions, making interference between macroscopically different histories practically impossible to recover. The branches are therefore not usually imagined as complete universes suddenly appearing in distant locations, nor are they separate bubbles floating somewhere beyond space. They are approximately independent components of one universal quantum state. The interpretation also does not say that every event a person can imagine must occur. Branching follows the alternatives permitted by quantum dynamics, not fantasy, desire, or arbitrary storytelling. Nor can an observer travel between mature branches, consult another version of themselves, or send information across them using any known process. The apparent multiplication of worlds is the price paid for keeping one simple dynamical law and eliminating a special measurement collapse. But that simplicity creates difficult questions of its own. What exactly defines a branch when decoherence is gradual rather than perfectly sharp? Why should an observer expect outcomes according to the usual quantum probabilities if every non-zero outcome continues somewhere? Supporters have developed arguments based on rational decision-making, symmetry, and the structure of branching, while critics debate whether these explanations truly recover probability without quietly assuming it. Many worlds is therefore neither established fact nor careless science fiction. It is a serious interpretation that reproduces the tested predictions of standard quantum mechanics while offering an audacious account of their meaning. Its deepest challenge is emotional as much as scientific. You experience one history, one memory, and one sequence of consequences. Yet the theory suggests that this singularity may describe only your position inside a much larger state. What feels like reality making one decision could instead be awareness. Following one branch after all, permitted outcomes have continued beyond mutual contact, leaving each observer inside a world that feels complete because every inaccessible alternative has become silent. Quantum physics works with extraordinary accuracy without explaining why reality feels definite. No scientific framework has predicted the microscopic world with greater success. Yet quantum physics still struggles to explain the most ordinary fact of your life. Everything appears to happen one way. Its calculations describe atoms, molecules, light, semiconductors, magnetism, chemistry, and particle interactions with precision so extraordinary that some theoretical predictions agree with experiments to many decimal places. Quantum electrodynamics, the theory of charged particles and electromagnetic fields, produces some of the most accurately confirmed numbers in all of science. The devices surrounding you work because these rules are dependable. Lasers emit controlled light, transistors switch, atomic clocks keep time, and medical scanners respond exactly because quantum theory correctly predicts how matter behaves. Yet the formalism naturally contains combinations of possible outcomes, while every experience you remember is definite. A detector shows one mark. A clock displays one number. A radioactive nucleus decays at one moment rather than all moments. You never remember observing a pointer occupying several visibly incompatible positions. Decoherence explains much of this transition by showing how interactions with the environment rapidly suppress observable interference between large-scale alternatives. It explains why certain stable states become repeatedly recorded and why classical behavior emerges so effectively from quantum systems. But decoherence alone leaves an interpretive gap. It transforms a coherent superposition into a set of alternatives that no longer interfere in practice, yet the mathematical description may still contain all of them. Why then do you experience one? Textbook collapse gives a rule for updating the state after a result, but does not clearly identify collapse as a physical event or specify an exact boundary where it occurs. Many Worlds says every outcome continues while each observer encounters only one branch. Hidden variable theories place definite facts beneath the quantum state. Objective collapse models add new dynamics that truly remove alternatives. Information-centered interpretations argue that quantum theory concerns expectations, records, or relationships rather than a hidden picture of reality. So far, no single account has won universal acceptance. This unresolved problem does not weaken the practical reliability of quantum mechanics. Engineers do not need philosophical agreement before designing a chip, just as navigators once used gravity successfully before understanding space-time. But the gap matters, because physics aims not only to forecast instrument readings, but also to describe what the world is. Quantum theory gives you an unmatched rulebook connecting preparation to observation, while the experience of one definite reality remains strangely underexplained. Perhaps definiteness emerges from entanglement, information, and the limits of observers. Perhaps collapse is a real process not yet detected. Perhaps every outcome persists, and certainty belongs only to the branch containing your memory. The final mystery is therefore not whether quantum physics works. It works almost unnervingly well.